So, improper integrals, my goodness, what in the world does this even mean? Well, typically, what we need for integrals to work. So normally for any sort of definite integral from like a to b of some function, what has to happen for this to exist for us before right now? For this to exist and us not have any problems with it, f of x must be bounded and finite on the interval a to b. That had to happen. What that means is that if I give you some curve, right? And I say, remember what an integral means? What's a different integral actually mean for us?
The area under a curve.
Good. Area under a curve between here and here. Basically, it says if I want to find the area under a curve of this curve from these two between these two numbers, our curve can't do weird things like between here and here go up forever. Well, that doesn't really make a lot of sense. Or it can't go up like this forever and have an asymptote. Or there can't be holes or weird things that happen. Basically, it says it's got to be bounded, doesn't go up or down forever. It's got to be finite, can't continue on in one direction forever. So basically, it's got to stop, it's got to start, it's got to stop, and it can't do crazy things in the middle. That's really what this sort of thing means. Do you guys understand the idea of bounded? It has upper limit, has a lower limit. It has right side limit, has left side limit, A and B. So basically, anything that's not like this is called an improper integral. We're going to study what those scenarios are and how in the world we're going to deal with them. So now, we're going to talk about two basic scenarios. So here, in section 7.6, we talk about these two cases. Case 1. Case 1 happens, well, suppose if you had an integral, you had some curve, and we said, here's our curve. Our curve goes like this forever. And I say, I want you to find the area under the curve from A to, and I don't give you a stopping point. If I did this, check it out. If I said A to B, from A to B, this would be fine. We'd have a curve that's bounded above and bounded below. Above by the curve, below by the x-axis. We'd have a starting point, we have an ending point. That's what this would say. It's bounded and it's finite. That would be cool. Does that make sense? But if I say, no. Now what I want you to do is take this function f of x, and I want you to find the area under the curve from A to infinity and beyond. Well, just joking. Forever and ever. Can we do it? Well, the problem is, the answer is yes, we can. I'm going to show you how to do that. The problem is, this no longer falls into this. It's bounded, sure. It is bounded. Do you guys see what I'm talking about being bounded? It doesn't go above a certain number. It doesn't go below a certain number. It's going to be asymptotic to the x-axis as x approaches positive infinity. But it's not finite. It starts at A, no problem. But it doesn't end. So it fails these conditions of being a normal definite integral. That's what makes it this idea of an improper integral. Do you guys get the idea of an improper integral? It's not finite, it's going forever. And likewise, I could go to negative infinity if I wanted to. So I could go this way. But this case is going to cover both of them. Or case number 2. Case number 2, so case 1 was the interval is infinite. Case number 2 happens like this. Suppose you have some function this is just for an example here. And I say, here's my function f of x. and I ask the question, hey, can you find me the area under the curve from a to b? Can you find the integral, basically, of this function from a to b? Can you do it?
No.
Well, let's see what happens here. Is the interval finite? Yeah. Interval starts at a, interval stops at b. That's cool. It's a finite interval. Does that make sense to you? Is the function bounded? Is the function between two actual numbers? That's no. We have a top bound. Top bound would be whatever that number is. But the bottom bound, it does not exist. This function goes to negative infinity on the y-axis. That's an issue right here. So case one is, well, if the interval is infinite, we have a situation, it's not a proper integral. If the function's not bounded, so here f of x is not bounded, that's our other case for an improper integral. So again, we got this idea of a definite integral. It works when a and b are finite numbers. So when we go from one spot to another, we have a starting spot, we got an ending spot. It works when f of x is bounded. This doesn't go up forever, it doesn't go down forever, within this range, okay? So it can be a polynomial for sure, which does either go to positive infinity or negative infinity. It's not asymptotic at all. But within the range, between this interval a and b, the function has to be bounded. You guys got that? The interval has to be finite. No problem. That means that's what we're talking about for a definite integral. If we don't have one of those cases, so in other words, if the interval is not finite, if it's infinite, goes to positive infinity or negative infinity or both of them, you can do both in both directions, that's one case where we don't satisfy these conditions, hence it's called an improper integral. It's not the way we want it. Or we have another case where f of x is not bounded within that interval. So we say, hey, here's our interval, but the function goes positive infinity or negative infinity within the interval. Basically, we've got an infinite discontinuity here. Does that make sense? Not a removable discontinuity. That would be different. It would still be bounded. But if we have a removable discontinuity, do you guys remember what those are? Those are just holes, right? Those are fine. But if we have an infinite discontinuity, that's an issue where the functions go into positive infinity or negative infinity. Hence, you have an asymptote somewhere on the interval. That's an improper integral. So again, two cases: interval's infinite or the function's infinite. It's unbounded. So hence, be okay with our two cases. Now, let's talk about how to deal with these with an example. We're going to talk about the first case first. We'll talk about for infinite intervals. For infinite intervals. Let's do it with an example. Let's see if you understand what I'm talking about here. Let's take the example of the integral from 1 to infinity. Oh, that already looks new, doesn't it? That's something we haven't ever seen before, probably, unless you've had this class before. You've never seen this before. Of 1 over x squared dx. Now, of course, this is the first time we're going through this, so I'm going to really teach it to you, try to make you understand what's happening here. The first thing we look for, and really you haven't ever had to look for this before in your integrals, but now we're going to because we're trying to do a definite integral, right? Well, it has to be defined on this entire interval. So let's check it out. What's a number that would not work or would be undefined in this problem?
0.
0 would be an issue. So, am I crossing 0 on this interval?
No.
Okay, so we don't have this situation, but check this out. If I wanted to go from -1 to infinity, do you see how I'd cross over a point where I'd be undefined? Basically, I'd cross over an asymptote. They'd go like this, at x equals 0. Does that make sense? That would be this case. We'd have some sort of an infinite discontinuity at that point, at x would equal 0. That'd be an issue. That would be case number 2. Does that make sense to you? Now, we don't have that. We're lucky. We go, okay, no. Let's just do +1. For this to work, well, no problem. It's got to be defined on this interval. It is. It's defined everywhere from 1 to infinity. Now, you have to understand that. We're good. We don't have this situation on this interval because, well, we missed the one point that's bad for us. We missed the 0. Now, let's check out the other thing. Let's check out the interval itself. Is the interval itself finite? Finite means it starts and it stops. Is it finite? No. It starts at 1. Where's it end? It don't end. Well, that's an issue for us. So which case are we in right now? Are we in case 1? Case 2?
Case one.
Case 1. So for an infinite interval, we're going to think about this a little differently. Let's say, you know what? Let's consider this. So let's consider not infinity, because that's really hard to think about. Okay, we don't want to think about infinity right now. Let's just call it b. So 1 to, I don't know, some number, b, of 1 over x squared dx. Where b is just some number that's bigger than 1. So notice something. I'm not saying b is smaller than 1 because this interval starts at the, remember how intervals work for integrals? Starts at the small one, goes to the big one. So let's consider this to be the integral from 1 to b, where b is simply some number bigger than 1. Basically, bigger than where we're starting at. Well, if that's the case, here's our picture. Our picture, if you know what the graph of 1 over x squared looks like, it looks like this from both sides. Now, I don't have to worry about this. I just have to worry about this side because I'm going from 1 to infinity. Our graph basically looks like this, where we're starting at 1, now, here's the little idea. The idea is, it's going to be really hard for us to legitimately go from 1 to infinity, because how can you actually plug in infinity for a definite integral? Did you guys see the problem? You can't really plug in infinity. You can't do it. So we're going to cheat a little bit. We're going to say, no. Let's not go to infinity. Let's just go to b. Now, since we're starting at 1, b's got to be some number bigger than 1. Does that make sense? So let's call this b over here somewhere. 1 to b. Well, then what our integral represents is this area from 1, the area under the curve from 1 to b, where this curve is 1 over x squared. So if you guys feel okay with that so far. I really do want to make sure you get the idea, not just be able to do it, but understand it. So the idea is, if we have an interval from 1 to infinity or negative infinity to some number, let's break this up a little bit. Let's not go to infinity. Let's call the infinite bound here, let's call it b, or if it was negative infinity, we'd call it a down here. Let's call it something. Well, maybe we go ahead and we do this integral the way it is now. Instead of plugging an actual number like 4, we're just going to plug in the b, and then we'll deal with it later. So we know that we can write this as not 1 to infinity, but 1 to b. b is some number just to the right of 1. We're representing this area right here. That's what we're doing. Quick head nod if you're okay with that so far. Let's go ahead, let's see if we can do this integral. I'm just going to rewrite it. So 1 to b, how would I rewrite the integral of 1 over x squared to actually do the integral? What would I do? Yeah. By the way, don't start doing silly things, hard things when you have easy integrals. Don't be doing weird things like partial fractions. I have 1 over x squared, partial fractions. No, don't do that. Okay? Don't make things harder than they are, which some of you have a tendency to actually do. Okay? So make the integrals as easy as possible. We know all the integration techniques right now, just so you know. We got them all. Now we're just applying them. Well, all for us. Can you do the integral? Sure. What is it? Don't all talk at once. I mean, that'd be rude. Okay, x to the negative
1. I mean negative 1.
over negative 1. Now, of course, with definite integrals, we evaluate these things. Well, we're going to change this around a little bit because right now it looks kind of nasty, but we're going to change it around. Where's this integral start? Interval start? Where's it end? Yeah, and we're calling it b. Really, it's going to be infinity, but we'll deal with that idea in just a second, okay? Let's rewrite this. So this is going to be negative 1 over x from 1 to b. Isn't it nice to deal with some of these easy integrals right now after doing all that stuff that we just did in this chapter? Can you evaluate negative 1 over x from 1 to b?
Yes.
What's it going to be? Good. We plug in the top number first. Minus what?
Negative 1 over 1.
Okay, let's clean it up. Negative 1 over b plus 1. Show of hands feel okay with that so far. That's easy, right? I mean, we've been doing this from Calculus 1. This is nice. Now, here's the issue.
Bless you.
Like a 10-second recap. 10-second recap is, this is improper because it's not a finite interval. This is cool because it is bounded on that interval. That's good news. That's the good stuff. So, bounded, yes. Finite, no. Infinite. Call the infinite portion of that, call it B, or call it A. Call it some letter. Usually we use B for positive infinity. We use A for negative infinity because intervals go from A to B. That's why. So call that B. All right, no problem. What B is some number bigger than 1. So since our interval is starting at 1, B's got to be to the right of that. And what our integral represents here is the area under this curve from 1 to B. No problem. That's exactly what this idea is about. Do your integral, plug in the B, plug in the 1, simplify it, but then let's think about what's happening. Now, when we did this, what did we substitute the B for?
Infinity.
So, what do we want the B to go? Where do we want the B to go? We want it to go to infinity. Now, the way that we deal with going to infinity is this idea of a limit. Limit. That's right, with a limit. So, as we want to go, x goes towards infinity, we can't do that by just plugging in infinity. We kind of can, we kind of can't. We can because that's really how we're going to evaluate this thing, but the way we need to evaluate it with is a limit. So what we do now is go, where's the B go?
To infinity.
Well, since we want B to approach infinity, we do that with a limit. So now we'll just let the limit do its work. So we're going to do a limit as x, sorry, I made a mistake. How did I make a mistake?
Yeah.
It's not x approaching infinity, it's
B.
b. The b is what we substituted in for our infinity. So now we just got to substitute it back. So b goes to positive infinity, negative 1 over b plus 1. Well, now hopefully it makes some sense. Let's let b go to infinity. What happens if b goes to infinity here? So, can we find the area under the curve from 1 to infinity of this curve 1 over x squared?
Yes.
That's really cool. How much is it?
1.
1. Yeah, that's the idea. So, this idea is, we're kind of cheating, we're not really cheating, we're really doing it perfectly mathematically. But the idea is, if you're going to infinity, just call it b, take a limit as b approaches infinity of whatever the integral is. That way you can actually evaluate. You can't plug in infinity, really. You can plug in b, then take a limit as b approaches infinity, and that's where we change the problem a little bit. Show of hands if that made sense to you. Is it a really difficult concept? Kind of interesting, right? Kind of cool. So let me write some notes out for you on what we're going to be doing every time. Questions? I always forget. Do you have any questions on this? Okay, good. Did I explain it well enough for you all to understand it?
Yes.
Okay. We'll deal with the unbounded version probably another time. But so here's what we know, some notes. Let's say we had an integral from a to infinity, or we have an integral from negative infinity to b of some function. What we do, we don't really do this every time, okay? Because what I've done, this is technically very inaccurate. Because what I'm calling this is b, but I haven't said anything that b is going to infinity. Does that make sense to you? So what we do right off the bat with our improper integrals, after we identify what's going on, whether it's discontinuity or whether the interval is infinite, we do that first. Then we go ahead and we write out the limit right now. You see, if we're going from a to infinity, then what I'm going to do right now is I'm going to say, which is the problem, by the way? Is it the a or the infinity?
Infinity.
So I'm going to say a to b. But in order to do that right away, what you should do is say, yeah, you know what? I'm going to take the integral from a to b, but I need to let b go to infinity. If it seems trivial to you, it's not. You're defining what's happening to the b. You have to do that. It's not that I just get to randomly plug in a b, figure it out, and then plug in infinity. You can't do that mathematically. You do that with a limit. So we say, no, we don't get to plug in infinity. Really, what we're thinking about is this b, it's approaching infinity. It's getting really close to it. It's plugging in bigger and bigger and bigger numbers until it makes no difference anymore as compared to infinity. Does that make sense to you? So it's not a trivial idea. It's, sure, call it a b, but then define what's happening to b. b is going to positive infinity. You do that with a limit. Now, the integral itself, this is where you guys get a break. The integral itself is doable. I mean, it's everything that we've done so far. So basically, the only thing I'm teaching you today is this. That's it. That you can do this. That instead of an infinity, you put a limit as b approaches infinity of b. This is still infinity when you think about it. We're just kind of making it a little bit more doable so we can actually evaluate the integral. That was a lot of words. Did you understand them all? All right. Now, next up. Let's say that we're not going from a to infinity, we're going from negative infinity to some b. What's our problem here? Okay, so the b is not a problem. We call negative infinity our a. And then we say, okay, cool. I'm going from a to b, but what's happening to the a? Where's the a going to go?
Negative infinity.
So a approaches negative infinity. That's right. It should match up. So a negative infinity, a negative infinity. And then the integral, no problem. You'll know how to do this. I'm not saying it's going to be easy, but you'll know how to do it. Because it's something that we've covered before. You guys okay so far? Now, we're going to come up with two different words here. Two words that I'm sure you've heard them somewhere in your life before, but for integrals, we're going to define them right now. These limits are either going to be what's called convergent or divergent. Now, if the limit exists, what that means is that you can add up all the little sums and it equals a finite sum. That would be a convergent integral. That means that the area actually exists. If the integral adds up and it keeps getting bigger and bigger and bigger and bigger, well, then that integral is not going to exist. That limit won't exist. Actually, the integral probably will exist, but the limit won't exist. If that limit doesn't exist, well, that's divergent. Either it doesn't go to a finite number, it goes back and forth, or it goes always up or always down. It doesn't go to one single number. If that limit doesn't happen, then we call that divergent. So these things are convergent if the limit exists, divergent if the limit does not exist. Does that make sense to you? Yes, no?
Yeah.
So we call these convergent. If limit exists. We'd say it's divergent if the limit does not exist. Convergent basically means this. I'll actually write that down, look up here so I know that you guys are done writing and can actually talk at you. Convergent basically means this. It means that the area that you're adding keeps getting smaller and smaller and smaller and smaller as you're approaching infinity or negative infinity. Smaller and smaller and smaller to the point where when you add it, it's so small that it doesn't make a difference. Does that make sense to you? So it keeps getting smaller and smaller and smaller and smaller. Divergent does this. Divergent says it keeps getting bigger and bigger and bigger as you keep adding it. Or it doesn't keep getting smaller and smaller and smaller and smaller and smaller. It doesn't do that. Or there's no pattern to it. It's bigger than smaller, than bigger than smaller, than bigger than smaller, something like that. So then the limit will tell us that. So don't worry too much about it. Basically the idea is, if the limit exists, it's going to be convergent because that idea is happening. It's getting smaller and smaller and smaller, quick enough. If it's divergent, if the limit doesn't exist, that means it's not happening. So we're getting bigger areas, or we're getting areas that don't go back to one single number. It keeps getting bigger and smaller, bigger and smaller. Does that make sense to you? Okay, would you like to do some examples? Of course you would. So let's do some. Thankfully, these examples won't take 30 minutes 30 minutes an example. They're fairly quick. Question.
Just kidding.
Was it on this?
I'm just kidding.
Oh, you were joking. Funny guy.
Is there ever going to be, like in case 2, where we'll be taking 2 minutes? like from negative infinity to infinity?
Absolutely. Yeah, I'm going to show you how to do every case I can think of. Okay, so that's why this lesson is going to be about 3 days long. Is that I'm going to show you everything that I can think of as far as what cases go. Okay, we're starting very easy right now, but we will have limits that go from negative infinity to infinity. We'll have limits that go from negative infinity to infinity where they cross over an infinite discontinuity. And that's about the worst case scenario you can get. Okay, so if you go from negative infinity to infinity and you cross over, if you cross over more than one, that sucks even worse. But if you cross over an infinite discontinuity, then you have to break up that limit the integral in at least 2 of them, sometimes more. Okie dokie? Okay, so let's start off very basic. Firstly, we want to identify what type of an improper integral, if anything, we have. Do we have an improper integral here? Absolutely. Well, firstly, let's see if there's an infinite discontinuity. Are we defined for an entire domain?
No.
Are we defined for an entire domain?
Yes.
Yeah.
I don't care about the 0. If I'm not crossing 0, I don't care. I care just where I'm going to. So on my interval, am I defined?
Yes.
Then we're good. There's no infinite discontinuity. Do you guys get what I'm talking about? How about the interval? Is the interval finite or infinite?
Infinite.
So what that's called is an infinite interval. That's one of these improper forms. So if we have an improper form and an infinite interval, let's write out exactly what we're going to do with it. So tell me, how should I rewrite this problem so that I can do it?
Limit.
Okay, so do you need the limit?
Yes.
I'm not going to check for that or anything on your test, am I?
Yes.
Of course I am. Limit. Hello. A limit from where to where?
B to infinity.
Oh, say that correctly. From where to where?
1 to A.
1 to,
B. All right.
and then B goes to where?
Infinity.
Perfect. Do we change this?
No.
Pull the 3 out.
Yeah, you can pull the 3 out. Absolutely. In fact, because it's a limit, and because that's a constant, you can actually pull the 3 way out here. Doesn't even matter. Pull it here, don't care. Wherever you want to go. Does that make sense? So we can pull the 3 out for sure. Can you do this
Yes.
integral?
Yes.
They're all going to be doable. Yeah, of course, for you. So we have a limit. We have B approaches infinity. I got to warn you in this section, because we've covered all of our integration techniques, I'm going to be doing a lot of them pretty quickly, because I'm going to assume that you have studied the previous 4 sections that we've done in integration techniques, okay? So I'm going to cut some steps out just for the sake of time, because we're going to get some integrals that are kind of nasty, you know? And I'm not going to repeat all those techniques that we just learned. I'm going to use them. Here, well, this is a pretty basic one to begin with. So what's our integral going to be here? 3 ln. Absolute value x. Oh, absolute value. Did you get that? From where to where? 1 to b. Now, be smart about the absolute value. Look at your interval. Your interval goes from 1 to infinity. Tell me something about all those numbers. They're all positive. So your absolute value is kind of irrelevant here, but you need to show it. So in our case, we've got a limit. Do you remember something about limits, how we always write them until the very last part where we actually get to evaluate them? Same thing happens here. So we will have 3 ln b minus, and you can do this a couple ways. You could pull the 3 out and have a bracket here, or you could have 3 ln b minus 3 ln 1. It really doesn't matter as long as you have the 3 in the appropriate spot in both places or being factored out. Make sense? Some algebra. So I'll probably do it like this because I don't want to have to write the 3 again. I'll do 3 times ln b minus ln 1. So this is limit as b approaches infinity of 3 ln b minus, how much is ln of 1? Do you know? 0. Okay, so check it out. Simple integral, no problem. We've evaluated, no big deal. We've simplified it as much as we can to the point where now we're going to attempt to find out what happens as b approaches infinity. You guys okay with this one? Awesome. So what happens when b goes to infinity? What's ln of b as b approaches infinity? Oh dear. Do you know?
Say that again.
Read it. What's ln of b as b approaches infinity?
0.
Nope. ln of 1 is 0. How can ln of infinity also be 0? That doesn't make sense. It's a increasing function the entire time. It's always increasing. Say what now?
Infinity.
Infinity. It's infinity. That's right. ln goes like this. Remember ln? I hope you remember ln. Goes to negative infinity as we approach 0 from the right, goes to infinity as we approach infinity. It's always increasing. What that means is that this is infinity. That's infinity. Tell me something about this integral. Is it convergent or is it divergent?
Divergent.
It's divergent. What that means is that, look at this. This limit keeps getting bigger and bigger and bigger, doesn't it? It means the area keeps getting bigger and bigger and bigger. It doesn't go to a finite number. Therefore, our area under this curve, we can't say what it is because it's an infinite area. It's called divergent. You guys see the difference between convergent and divergent? The first one we did, we actually got an area out of it. Second one we did, no. This right here says that this is divergent. And I wanted to give one to you right off the bat. That way you see what I'm talking about when I say divergent. If the limit doesn't exist, or if the limit goes to infinity or negative infinity, then we say that we can't find the area under that curve. It's always getting bigger than some finite number. Show of hands if that one made sense to you. Okay, can we keep on rolling? Not too bad, right? Not yet, at least. Let's keep going. What we're going to do now is we're going to figure out how to do this in general for any power of x. So instead of doing example after example, let's try this one. Let's go from 1 to infinity, 1 over x to the n dx. You know what, I'm guessing that most of you can probably help me out on this one. What's the first thing that I would do with this particular integral? Write a limit, yeah, because tell me what's wrong with it. Do I have a discontinuity or an infinite interval here? It's an infinite interval. Do you notice how in this case, the only number that I have a problem with is 0 still? I missed the 0 on my interval, so I'm good. So yeah, you know what, we just had it on the board a little while ago. This will be a limit as what approaches what, everybody?
B approaches infinity.
And then we write from where to where, please?
1 to B.
1 to B.
And then,
1 over.
okay, yeah, okay. We'll do another step. Sure. Can you guys do that first step? Hello, yes, no?
Yes.
No big deal, right? You just take care of the infinity, make sure you have a limit, go into that variable, and then take your variable and make it look like it's finite right now. Make it look like it's going to an actual number, just something bigger than 1. Now, let's go ahead and do this in general. I know that some people don't really like doing things in general, but this is going to save us a lot of headaches later, so check it out. First thing we could do. Always, it's going to get annoying, I know, but you always got to write the limit. You always have to do that until you actually evaluate it, so do not neglect that. Are you listening?
Yes.
Don't neglect that. Always write it. Now, with 1 over x to the n, I can write that as x to the negative n dx. You see, if I have x to any power besides 1, I can always move that up. And I can always do this integral. Notice that we already took care of, if you didn't notice this from before, we already took care of the case when we have 1 over x to the first, don't we? Already took care of it. In fact, the 3 is irrelevant. If the 3 was a 1, you would still have something that's infinite. Do you see what I'm talking about? Hello, yes, no?
Yes.
So even if this was a 1, no problem. So basically, what's 1 to infinity of 1 over x dx? It's also divergent. It's also a problem. Okay, so we already kind of dealt with that case here. Let's look at every other case. If we do this, we'll get a limit as b approaches infinity of, when we do this integral, what do you do with like x to the third, or x to the negative third would be a better, you add 1. So this would be x to the negative n plus 1. Negative n plus 1. Sure. That's exactly what we do. We add 1 to the, remember doing that? We add 1 to the power, divide by the new power, so we do all the time. And then we evaluate it from 1 to b. Well, if we evaluate it from 1 to b, we have a limit as b approaches infinity. Tell you what, I'm going to change this around because I like the look of 1 minus n better than negative n plus 1, just me. We're going to have, remember where the b goes. The b is going to go in terms of not n. N's going to be a constant, okay? B is going to go in terms of x. So this would be b to the negative n plus 1 over 1 minus n minus 1 to the negative n plus 1 over 1 minus n. Are we okay with that one? I want to make sure that you guys are good with this before we go on any further. Are you? You sure? So, hey, add 1 divided by the new exponent, no big deal. Plug in the b. We got it here. Plug in the 1. We got it here. It's got a common denominator. Let's simplify this just a little bit. So if we simplify, we got a limit as b approaches infinity. Well, in here we have b to the negative n plus 1 minus 1. Notice that 1 to any power is still 1. Over 1 minus n. You know what we can do also? Anytime you don't have the specific variable that this is approaching, the specific variable is right here like b, you can pull out everything in front of your limit. So I'm going to pull out the 1 over 1 minus n. You can rationalize this because, well, n is going to be a constant, isn't it? So this is always going to be just a fraction. Pull out the fraction.
Question.
Now, let's see how I want you guys to see this next. I'm going to do a little bit of fancy pants math because it's going to be easier for you to see what happens next. Are you ready for it? I'm going to force this to factor out a negative. So what I'll end up getting is, I'll move down here too. 1 over 1 minus n times the limit b to the negative infinity. I'm going to force this to be b to the negative n minus 1. B to the negative n minus 1. Do you guys follow the math on that? Okay, minus 1. Probably need some parentheses here just to show what's happening. I'm also going to write this as a fraction. Limit as b approaches infinity. Because this is now a negative exponent, what I'm going to do is I'm going to write this as 1 over b to the n minus 1 minus 1. We okay with that one? Are you sure? Some of you guys are zoning out. Don't zone out now, man. You got to be with me here. So, you okay with factoring out the negative from the exponent?
Mm-hmm.
If we have a negative exponent, hey, you can write this as 1 over b to the positive exponent. That's all I've done here. So, 1 over 1 minus n, no problem. Limit, limit. This is this minus 1 minus 1. So far, so good?
Yeah.
Now let's think about this for a second. When is this going to converge? When is it going to diverge? Because we want to do this once and for all. So let's think about this. Let's say that n is, well, how about we get n is 1? If n is 1, think back, just stop with me for a second, okay? If n is 1, then this was 1, correct? Are you listening?
Yes.
I need your attention here. If n is 1, then this was 1. We've already dealt with that case. We know it's divergent. Does that make sense? So we're going to have anything that where n is 1 is divergent. If you got that here, you'd actually get infinity to the 0. It turns out that when you do, remember our indeterminate forms? When you did that, you'd end up getting undefined out of that. You get infinity. So that would be an issue for us. So n equals 1, we know it's divergent. How about n equals 2? Let's think about n equals 2. If n equals 2, what's 2 minus 1?
1.
This would be like infinity to the first power. That's infinity. What's 1 over infinity?
0.
This would be convergent. You'd actually get a number out of that. How about 3? What if n is 3?
2.
Same deal. Or 4? Same deal. Or 5? Same deal. Now, we already did the 1, correct? What if n was 0? Or negative 1? Or negative 2? If n is 0, we'd get 0 minus 1. How much is that? Negative 1. So basically we have b to the negative 1, wouldn't we? that would be b to the first up here. That would be infinity. Do you guys get what I'm talking about? So we get this statement. I'm going to write it right up here. So from all this stuff, we know a couple things. So, let's think about the integral from 1 to infinity of 1 over x2. I don't care what it is, you can do it now. Without, well, you can't evaluate it, but you can see whether you should evaluate it or not. So, check it out. Let's say that x was to the first power. We already dealt with that. That was divergent. Let's say x was to the second power, so n was 2. We talked about that. That would be convergent, or 3, convergent, or 4, convergent. Basically, this is convergent if n is greater than what number, please? 1, yeah. Not equal to 1, but greater than 1. If n is 2 or 3 or 4 or 5 or 6, then we have infinity to the positive power. Infinity to a positive power would be infinity. 1 over infinity is 0. 0 minus 1 is, oh, negative 1, no big deal. That would be negative 1 times whatever this is. Does that make sense? Now, that's kind of cool, right? It gives you almost a formula for doing that. Cool. Now, let's say that n was equal to 1. We talked about that. If n equals 1, I have an ln. We just did the ln. That diverged. If n is less than 1, if n is less than 1, we'd have 0, or negative 1, or negative 2. We'd get b to a negative power. Is that, are you with me? B to a negative power is the same thing, under 1 is the same thing as b to a positive power by itself. Infinity to a positive power is infinity. Infinity minus 1, I don't care what you do, it's still infinity. That's an infinite limit. That limit is not going to exist for something that's going to be convergent. So, basically, this converges if n is bigger than 1, diverges if n is less than or equal to 1. That's the idea. So, here's what I'm trying to tell you. If I give you this, should you bother to find out whether this thing has a limit or not?
Yes.
Absolutely, because that's a positive exponent. That's that n equals 3. No problem. It's bigger than 1. But if I give you this one, would you bother?
No.
Heck no. You know automatically that's going to be divergent. For sure. Don't even worry about it. Just say, oh, look at that. N's less than 1. Hello. Divergent. Or if it equals 1. If it's that, you go, don't even need to worry about it. That's going to be divergent. You with me?
Mm-hmm.
Okay, so that's kind of a nice little thing that we can do here. Just look at that. Did it make sense to you, this whole explanation? There's one more thing I was going to say. I don't remember what it was. It must not have been that important. Oh, yeah, I know what it was. What that basically says is that because all of these negative powers are going to be divergent, change that into a positive, and what you end up getting is x to the 4th dx, don't you? You get a polynomial. Do you realize that if I take an integral from 1 to infinity of any polynomial, polynomials don't have negative powers, okay? Any polynomial. Polynomials go like this, they go like, or they go like this. That's their end behavior. It's either positive infinity or negative infinity. Are any of those limits going to be convergent for us?
No.
They're going to exist, but they're going to be positive infinity or negative infinity. They're not going to exist to a finite number. Therefore, these integrals will all be divergent. Does that make sense to you? Okay. We're going to stop there. We'll continue with this next time. All right, let's get started on our next example. The next example is another case of where we have these infinite intervals, where we're starting at a number or we're starting at infinity, but we have one section that's defined, like one part of the interval is defined, and one section that's not. So here we have, we're starting at 1, but we're not ever ending. We're going to infinity. Do you remember what we do right off the bat when we have a scenario like this? What's the idea? It's a limit, that's right. So what we're saying is that no, we really can't go to infinity the way we want to because we can't really plug in infinity since we don't know what it is. But what we can do is we can say, all right, well, I know I can take a limit from, what's our problem here? Is it the 1 or the infinity?
Infinity.
Yeah, of course it is. The 1's great. The infinity, we call that some letter. We typically call the upper bound b and the lower bound a. So if your infinity is in the upper bound, call it b. And then what we say is, all right, well, this is fine. This now becomes something that we can use a definite integral for, where b is a number. The limit idea says, okay, now you're going from 1 to some number bigger than 1. This is the idea. Then the limit says, okay, now take that number that you're going to, where we called it b, and move it forever to the right. So move it forever towards infinity. And that's why we have to have this limit here. And then the rest of the integral, well, that doesn't change. After that, the nice thing about these, well, we know integration techniques. That's what we spent all this time doing, which is fantastic. Question?
If we just avoid writing that to the end, is that technically incorrect?
Yep.
Okay.
Yep, you have to write the limit. You have to have everything I'm showing you is what you need. Because if you just go from 1 to b, that doesn't make sense.
Oh, I meant just avoiding the b altogether until you do the actual.
You could do the integral first. I prefer you doing the limit. This is what's going on here. We're changing to a definite integral where b is just some number to the right of 1 or whatever number you're given. Then you do it, and then you evaluate with b, and then you take your limit. Really, that's a proper form. Super big deal for some people. I don't know. I'd like you to do it this way, though. Okay? So, continuing. Can we do an integral like that one? Hello, can you do the integral? And that's pretty easy. What are you going to do with it? Too bad. I deal with a lot of people who come up with questions going, man, how do I do this? And I'm looking at them, man, you guys are making this way too hard. Way too hard. Start with the easy stuff. Calculus is supposed to be, well, how can you make it easier, all right? So when we look at this, we're not thinking integration by parts right off the bat or whatever. We're thinking, well, do basics. Is it in your integration table? Well, no. Can you do it with a U sub?
Yes.
Yeah, do a U sub then. Do something simple if you can. So with us, we go, okay, cool, well, we can do U sub. So u equals negative 2x, du equals negative 2 dx, or du over negative 2 equals dx. Something really nice. What that means is we get the limit. Forgot the limit. We get the limit as b approaches infinity of the integral from 1 to b. What's going to be on the inside of our integral?
E to the U.
E to the u. That's right, e to the u. And then dx, no, we got du over negative 2. This is actually kind of a pleasant break for us as far as dealing with some simple integrals, isn't it? Kind of nice, where we know how to do these. They don't take 4 pages for one problem. What are you going to do now? What do you think? Okay, so you know what you can actually do? I don't know if you know this, but you can bring that negative 1/2 to the front of your integral, but you can also do it to the front of the limit. So whatever you want. If you want to bring it all the way out front, you just do negative 1/2 times the limit as b approaches infinity. I'm also going to do the integral. So we pulled out the negative 1/2. What's the integral of, remember this would be gone, right? This is our negative 1/2. What's the integral of e to the u?
E to the U.
I love that integral. And then where are we evaluating?
From 1 to B.
Yeah, 1 to b. Notice how if we pull out that negative 1/2, it makes what we're evaluating just a little bit easier. It's kind of nice. We don't even have to worry about that. It's just going to be negative 1/2 times the limit. Quick head nod if you're okay with that so far. Now we get to evaluate. So what we know is that we're going to have negative 1/2 times the limit as b approaches infinity. Let's evaluate. What goes first, the 1 or the b? E to the b minus e to the 1. Now, if you're going to do these correctly, you do have to be very good at understanding what's happening to these functions as you approach infinity. Some of you struggled with this when we dealt with limits the first time. Would I mess it up?
What about, the U substitution?
Oh, my bad. It's actually going to matter here too. I got all wrapped up in talking about infinity. I forgot my substitution. You know what I mean? I was just testing you. You passed. Fantastic job. What do you do here then? Okay, yeah, so before we evaluate, you should have caught me earlier. Thanks a lot, guys. Limit of e to the negative 2x. Yeah, good. Why is that important?
Because
Yeah, you know, typically what I do in my substitution problems, I change bounds. So if you're used to doing it like I was, don't make the mistake that I did, where you forget to substitute back in for that u. That would have been a really big mistake. I'm glad you guys caught me on that. Did everyone see the mistake that I made? Okay, it's on video. Watch it again. You can see the mistake that I made. All right. Yeah. Make sure that you're actually doing that substitution back, because if you haven't changed your bounds, that's a must. You have to do it. So, very good job. Nice catch. So -1/2 limit as b approaches infinity. What we end up getting is e to the -2b minus e to the -2. You still okay so far?
Yes.
Well, maybe what we want to do is make this so it's a little bit more understandable on what's going on with our functions. So if you can do it from right here, cool. Go ahead and evaluate your limit from right here. If you're the type of person that says, you know what, I really don't like dealing with all these negative exponents, that it's hard for me to do. Well, then what I would do if I was you is I'd keep the -1/2 out front, I'd write the limit as b approaches infinity, and then I'd rewrite these two things, because maybe that's going to be a little easier for you. How can you rewrite e to the -2b? What could you do? Minus?
1/2 squared.
Yeah, maybe that's a little bit easier to see what's happening. Now, back to my point that I skipped over, an important point to make. My point is this: you're going to have to be really good at determining what's happening to your function as you approach infinity, or negative infinity. It's really important to do that. So when we look at this, what happens to e to the 2b as that b goes to infinity? What's happening to that? This little piece goes to infinity. Remember what e looks like? E looks like this. So as x goes to infinity, e is going to infinity. What that means is that if we have 1 over, so infinity, 2 times infinity is infinity. E to the infinity is infinity. How much is 1 over infinity?
0.
Yeah, this thing goes to 0. 1 over infinity is 0, for sure. Now, what's this thing go to?
Just b squared.
Nowhere. This is it. It's a constant. So what that means is that we're going to have this -1/2 times. Notice how when I evaluate the limit, when I evaluate as b goes to infinity, I stop writing limit, but I don't do it until I actually evaluate it. You guys clear on that one? We do have to have it every single time until we get down to, oh yeah, okay, when b goes to infinity, this thing goes to 0. Then in here we have what?
0 minus.
Okay, 0 minus 1 over e squared, which is equal to, let's do it, -1/2 times 0 minus 1 over e squared. How much are you going to get? Negative positive. Which one? Positive. 1 over 2 e squared. What I find just amazing about this is that what we really did here is we found the area under a curve. What curve? This curve. We found an area under this curve from 1 to infinity. So starting at the number 1 and going forever, and we got a legitimate area underneath that thing. Isn't that interesting? It means that we're getting so close to probably 0 as we go to, or some numbers go to the right, that it doesn't make any difference when we add that. That's cool to me. I don't know why that's cool, but it's so cool. Is it cool to you that we can add something up from 1 to infinity and get an actual number? By the way, did the example make sense to us? Good. Do you guys want to keep going? We're going to make it a little bit more difficult as we go. Well, not more difficult, but more involved, I suppose. I want to give you some different cases. So let's continue. So I guess long story made real short, the integrals are going to be very similar to what you've done before. The only idea is you need to identify what type of improper integral we have, whether we have an infinite interval or an infinite, emphasize the wrong syllable, an infinite discontinuity there. So whether we have a discontinuity or infinite interval. So in our case here, when we get this one, what do we got? Do we have an infinite discontinuity, or do we have an infinite interval? Which one? Both. Neither. One or the other. What do you think? Do you know? I want you to think about sine. Are there any problems with sine ever? Do you ever have a discontinuity on the function sine?
No.
Never. It goes like this forever and ever. So from 0 to infinity, are we going to have an infinite discontinuity? No, we're good. It's going to be defined for this entire range of numbers because it's always defined for the entire interval of numbers. Does that make sense to you? Now, we do have a situation here. We have, well, we've got the infinity. This would be called an infinite interval. So I want you to do the first step. Write this as instead of going from 0 to infinity, we're going to go from 0 to what?
B.
And in order to do that, we add this little thing in front of our integral. What is it?
The limit.
Okay, so you should have done that already, or be doing that right now. So we think about this and go, no. Let's just start at 0, because that's good. But let's go to some number just to the right of 0. And then let's take that number and push it to infinity after we've done the integral. So we're not really cheating, but we're kind of manipulating our integral properly. So we're saying, hey, let's go from 0 to b, that way it's definite. It's a definite integral. This says now, at the very end, take your b and push it to infinity. That's the idea. Now, I know that we've been dealing with some really difficult integrals, so don't make these harder than they actually are. Don't do anything fancy for the integral of sine x. What's the integral of sine x? Awesome. So we're going to have a limit as b approaches infinity, negative cosine x from 0 to b. Let's plug them in. We're going to have a limit as b approaches infinity, negative cosine b, okay, minus negative cosine of 0. Let's see what we get out of this thing. So negative cosine b plus cosine 0. Let's start with the easy part. What's cosine 0? How much is that?
1.
So we know this is going to be equal to 1. Now, think about negative cosine b. Think about just cosine b. What is cosine b as b approaches infinity? What is it?
Keeps going back and forth.
Cosine. Cosine does, negative cosine. Negative cosine does... Does it ever go to a number?
No.
No, it's going to go up and down and up, forever and ever and ever, correct? So my question is, as b approaches infinity, does cosine b ever go to a single number?
No.
Goes through lots of numbers, goes from a range of negative 1 to 1. So if it doesn't ever go to a number, does the limit exist?
Divergent.
It's divergent. This limit doesn't exist because cosine does this forever. It doesn't ever go to 1 or negative 1 or some number between there. This is a DNE type of limit. If you get a limit that does not exist, what do we know about the area here? What do we know about that? Is it going to be a convergent integral where we can find an area, or a divergent integral where we can't find the area?
Divergent.
So this is what I meant about those cases. So where we had convergent or divergent. If we have an integral that equals some function that when we evaluate we get a single number, like we did here, this would be convergent or divergent? So if the limit exists, it's actually equal to a valid number, like this one. We have an integral that's convergent. Our improper integral would be convergent. Show of hands if you feel okay with that idea. Convergent means the limit exists. If you get an integral so that when you evaluate with our limit here, we get something that doesn't exist like this one, it doesn't actually get to a number, or something where we have infinity or negative infinity, that's when we get this divergence. So there's basically three cases. The cases are, we get an actual number with our limit, we're good. That meant convergent. The other two cases are divergent, where we have a limit that does not exist, because it doesn't go to a single number, like cosine doesn't, or where we get an infinity or a negative infinity. That limit, it exists, kind of, but it's not an actual number that we call convergent. It's just ever growing or ever decreasing. Show of hands if you feel okay with the idea. Okay, so here we'd say this integral is divergent. You know, you might have guessed that just by looking at the function itself. Look at sine. Does sine ever go to a solid place? really. It's always going back and forth. So if you thought about what integrals actually mean, integral means area under a curve. So if we're thinking about, hey, you know what? I want you to find the area under the curve from 0 to infinity of sine. You're going, all right, well, there's going to be an area, then very little area, then more area, then very little. What's going to happen there? You know, it's going to go forever like that. You're never going to be able to tell me how much the area actually is. So far, so good? Okay, cool. Have I explained these two well enough for y'all to understand them? You guys have any? I'm going to ask you now before I erase them. Any questions on these before we get going? Okay, so doesn't exist, it's divergent. If the limit does exist, it's convergent. We're good to go. We can actually find the area. That's very cool. Let's continue. Can we ramp them up a little bit? These ones can get kind of boring if we do simple integrals all the time. So let's see how this works with something a little bit funner. Okay, first duty. First duty we got is to define what type of, are you laughing because I said duty? You guys watch too much Scrubs. Anyway. What was I saying? Duty.
First duty.
The first duty. Should be the second duty. Anyway, first duty is to define what type of improper integral we actually have. Whether it's an infinite interval, whether it's an infinite discontinuity. Here, this is all defined for the entire domain. X and times e to the x, we're good to go. We have no issues here. So it's not an infinite discontinuity. Those should be kind of obvious to us when we get them. You'll see them. What we do have is an infinite interval. We actually start, though, at negative infinity. So we're going to do something very similar to this idea, only I'm not going to be going from a number to b. I'm going to be going from, how would I write this?
A.
Okay, so because our lower bound is an infinity, I'm going to call that a. 0, I'm good with the 0. We're just going to go from a to 0. Does that make sense to you? Now, of course, we got to define what we're actually doing here. So, yeah, I can't just go from a to 0 and not define what a is doing. What's a doing?
Approaching negative infinity.
Good. Let's make sure we get that negative infinity in there. And that means the only way we can do that, to let a approach negative infinity, is with this idea of a limit. Quick head nod if you're okay with that one. So typically we call our upper bounds b's, we call our lower bounds a's if they are positive infinity or negative infinity respectively. After that, what's really cool, again, is that we know how to do all these integrals. So let's go through this integral. Right now is the time we go, okay, well cool, we define what's happening here. We now have a definite integral, and then we're going to let a go to negative infinity to take this idea of negative infinity to 0. But we just got to worry about this right now. So the integral of x e to the x dx, let's go through what we know. Does it fit the integration table? Can you do a substitution with it?
Nope.
Could you do a substitution if I did this?
Yeah.
That would be nice, so that's what we would do in this case. If I don't have that, then no, we can't do a substitution. Can you do integration by parts?
Yes.
Yes, you can. It's a product. We can do integration by parts with it. So, let's do integration by parts. What would you pick? What would you pick for? Do you remember how to do integration by parts? It's been a while, so this is one of those things that you should kind of do from time to time on your own, whether I give you homework or not, because we haven't really covered that in a long, long time, all right? But it is part of this chapter. So, what would you pick?
Yes.
Yeah, u is x. Remember how to pick u? You want to pick these u and v this way. You want to pick so that you can do the integral of what's left over very easily, and that the derivative of u becomes easier. So here I'd say, hey, can you do the integral of x? I can,
Yes.
but it gets worse. It gets x squared over 2. I don't want that. Can you do the integral of e to the x? And the integral of e to the x is?
E to the x.
Okay, that's nice. Can you do the derivative of e to the x?
Yes.
That's e to the x. Doesn't get nicer. Can you do the derivative of x? That's nicer. So our appropriate choice here is u equals x, and then v equals, the way I always teach this, I say, hey, cover up your u. V is the integral of whatever's left over. So du equals dx, v equals e to the x, because that's really nice. And then do you remember the formula for doing integration by parts? Honestly, I heard it was du. Okay, very good. V du, very good. So So we have, you know the annoying part about this is we still have to write the limit, because that's really still what we're doing, okay? So we've got a limit. We've got a approaches
Negative infinity.
negative infinity, that's right. Now, in this limit, we don't have the integral anymore. We have, well, our integration by parts says we do a u times v. So what are we going to write first?
X.
Very good, x times e dx. You guys with me still so far? Minus the integral, good. So u times v minus the integral of v du. But du is dx. So we have integral of v and then du is our dx. Show of hands feel okay with that one. By the way, for those of you who are thinking, well, what about our bounds here? Don't worry about it. You're going to evaluate later. Don't evaluate this integral right now. Wait till you do it, then evaluate the entire thing from a to 0. Does that make sense to you? If you try to do it here, it just makes it too hard, okay? So wait on it for a second till the very end, till your integral's actually done. You got that? Otherwise, you're really working overboard. So I am going to put this here. I'm going to put the a to 0 so don't forget about it. But I know I have one more step in here to do before I actually evaluate that. So I'm going to have a limit as a approaches negative infinity. I have x. I've got e to the x. This is why integration by parts works so nice for this. We reduce the power of our x by 1 degree. If we've done that, then that means the rest of this integral is really nice for us. What is the rest of that integral for us? Minus what? From? What are we going to do now? What do you think? We could simplify, we could factor if you want to. Sure, you could factor this. You could do it right now if you want to. It doesn't really matter to me how you do this. If we do decide to factor this, since you guys said that, we'll have a limit as a goes to negative infinity of what?
e to the x times x minus 1.
Perfect. Okay, well now let's go ahead and evaluate that. So, what we've done so far is first thing we do, we identify that we actually have an improper integral. We find out the type, whether it's the infinite discontinuity, we haven't even talked about those yet, or an infinite interval. If it's an infinite interval, no problem. We know how to do that. Let's just take a limit, and instead of the infinity, we'll make it definite for like the right now. It's a definite integral right now. That means that we can actually do it, okay? By the fundamental theorem of calculus, this actually works. So, we do this so that this is actually possible. Then we realize, oh, but you know what? B wasn't actually definite. B was this number that we want to now move to infinity, or A was this number that now we want to move to negative infinity. So we're cheating a little bit. We're calling this a definite integral when we know it's not. But it uses the fundamental theorem of calculus to actually do the definite integral, and then says, now use the limit idea. Now move that number to infinity or negative infinity. Hey, just evaluate the limit. So when we do, we're going to evaluate the integral, but then evaluate the limit. So a is going to eventually go to negative infinity. We got to plug it in first to see what happens. Which number do you plug in first?
Sure.
Make sure you do that, okay? Make sure you follow the rules for evaluating your integrals here. So we'd have e to the 0 times 0 minus 1 minus e to the a times a minus 1. Okay, let's simplify some stuff here right now because I have no idea what's going on with this. I gotta simplify this because right now it's a little bit too confusing for me. Do you guys see what I'm talking about? A little bit too much going on. So, what can we do with this thing? E to the 0 is how much?
1.
Good. 0 minus 1 is? So this whole piece, it's 1 times negative 1. This thing goes to negative 1. Very good. Also, I'll tell you right now, what's going to happen here, because I have infinity and infinity, I'm probably going to want to distribute this real quick. So, might have been nice if we hadn't have factored that, but you know what? Not a big deal. We can take care of it right now. So in our limit, we've got negative 1. We're going to have minus a times e to the a, and then plus e to the a. Can you check my work? I want to make sure that my algebra is correct too. Can you check that to see that I'm okay on that one? Are we okay with that? So I've distributed this. This is a e to the a minus e to the a, but then my negative changes the sign. So minus a e to the a and plus e to the a. Show of hands, feel okay with that so far. Now let's think about what's going on here. Do not neglect your knowledge of limits from your chapter 6 stuff that we've done, okay? You've got to really follow that. So if we look at this, part of this is really easy. So check out the -1. What's that going to go to? That's easy. Check out the e to the a. Oh, let's think about this. E to the a when a approaches negative infinity. So basically, what's e to the negative infinity? 0. It's 0, that's right. So this is 1, -1. This is 0, that's fantastic. Now, please listen carefully. This is a times e to the a, correct? We already know that this part is 0. E to the negative infinity is 0. But this is negative infinity. So we have an infinity times 0. That's an indeterminate. Oh, remember that? Oh, it's coming back. This is exciting. It's an indeterminate. Look at how much stuff is involved in this. Had you not done indeterminate forms, you couldn't do this problem. Had you not done integration by parts, you couldn't do this problem. And now we have improper integrals. So we've got lots going on in this stuff. This is why this calculus builds so nicely for us, but you got to remember it, all right? So it's not like other classes where you can forget a section and you're probably okay. You need everything to do these problems sometimes. So for us, we go, all right, well, cool. This is easy. -1. This is easy, 0. But this one, well, that's an infinity times 0 type of indeterminate form. What that means is when we have infinity times 0, we've got to rewrite one of those in order to get an infinity over infinity or a 0 over 0. In either case, we can use L'Hopital. Remember L'Hopital's? It's a favorite word in limits. L'Hopital. So I'm going to do something here. I'm going to separate these. What I know is that this is cool. This is -1. This is also 0. So I'm going to do this. I'm going to separate these limits. I know I'm going to have -1. I'm going to have minus the limit a times e to the a as a approaches negative infinity plus 0. So basically, I just want to focus on this guy. I want to see if you guys are okay with the math on that. Are you okay on where the -1 came from?
Yeah.
That's this limit. Limits are separable by addition and subtraction. This is 0, no problem. I'm just focused here. My minus is right here. So I have a limit as a approaches negative infinity of this guy. Just that guy. Quick show of hands if you feel okay with that one. Now, if you don't remember how to do these 0 times infinities or infinity times zeros, rewrite this as a fraction. So take one part of this and move it to a denominator. Now what I know is that it's going to be easiest if I move this e to the a to the denominator. So I'm going to take a little break here. We'll call this asterisk. The limit as a approaches negative infinity of a times e to the a can be rewritten as the limit as a approaches negative infinity of, I'm going to keep the a. I'm going to keep the a right where it is. But the e to the a, I want to rewrite that. Can you tell me how can I write a times e to the a as a over something?
To the negative.
Yes. In your heads, is this the same as this stuff? Now, check it out. Remember whenever we change something in our limits? I don't know if you do remember, it was a long time ago, but if you don't remember, rewatch the end of chapter 6, okay, on the video, and it will show you all this stuff. This was the indeterminate forms. Whenever you do something algebraically, you reevaluate it, and you see what actually happened. So if we reevaluate this, how much is a as a approaches negative infinity? Now, how much is e to the negative a as a approaches negative infinity? Remember, a negative times negative is a positive. How much is this?
It's infinity.
It's infinity. So we have a form of infinity over infinity. Does that make sense? This is a prime candidate for...
L'Hopital.
Yay, L'Hopital. It's a fun word even. So L'Hopital. Can you explain to me, please, how you do a L'Hopital's rule? What do you do?
Take the derivative of the top over the derivative of the bottom.
Cool. Is it a quotient rule?
No.
Heck no. Derivative of numerator is, this is why we left the a where it was, okay? If we made it 1 over a, our a power would grow and our e power would not decrease. So that's why we left the a where it is, because the derivative of a is 1. That's beautiful. The derivative of e to the negative a, can you tell me what the derivative of e to the negative a is? Some of you said e to the negative a, some of you said negative e to the negative a. Which one's right?
Negative.
What gives you that?
Chain
Chain
rule.
rule. Oh my gosh, we even have chain rule in here. So derivative means you leave it alone. You leave e to the negative a alone, but you multiply by the derivative of whatever function's inside there. This is a function of a. Derivative of negative a is -1. Now, can you evaluate this limit? Now, yeah, sure. How much is e to the negative? So what was that again? E to the negative a as a approaches negative infinity. Oh my gosh! So check it out. If a goes to negative infinity, you've got negative infinity there, right? Negative infinity is e to the infinity is negative infinity. I don't care what it is. If it's infinity, if it's a number over infinity, you get how much? This is 0. Now this was our asterisk, so we'll move it right back up here. So what our limit is what do we have left on this thing?
-1.
This whole thing went to 0. What's really, I don't want you to forget what we're actually doing, okay? A lot of people in calculus, they end up learning how to do this stuff, but not really what you are doing. What do we just do here? What do we find? Area under this curve from negative infinity all the way up to 0. And how much is it equal to? Interesting. That means it's below the x-axis. That's what that area means. The majority of it's below the x-axis. Show of hands feel okay with this example. So we do, hey, infinite interval, no problem. Make it definite. Just define what's happening. This means that we can actually do the integral by integration by parts, or whatever we have here, integration by parts, saying, hey, u is x, v equals integral of the rest. Do integration by parts, u times v minus integral of v du. Evaluate that thing once you've done the complete integral, not right here, but after you've done the whole thing. Evaluate it, then simplify it, and then work with your limit. Haven't you covered all this stuff before?
Yeah.
Oh, and nothing's really new. Nothing. It's just putting it all together now. Sure you're okay with it? Okay. Can we move on a little bit? Do it. Finally on a roll. These problems don't take 45 minutes of problem like before, which is nice too. You're going to love that on your homework, I'm sure. Well, except for this one. What? K? K? Why? ¿Por qué? Why do we do this? Why do you want to murder us? Oh my gosh. Let's think it through. Let's think this through. First thing, are we defined, because we always check this first, okay? Look at your function inside of your integral. Is this function defined for your entire interval? If you say no, then you better give me a number that doesn't work here, and you better be right. So if you just guessed at it and said, because it looks funny, probably not the best thing to do, all right? So why don't you think about it? Is there anything that gives us a problem in this function? Is e to the x defined everywhere?
Yes.
Yes, so this is fine. Is e to the 2x defined everywhere?
Yes.
And if I add it to 1, do I have a problem in my domain? No, this is defined everywhere, but that's what I'm asking you to check. You got to be good with finding domain. This is why your teachers taught you how to find domain. So you go, oh, you know what? My domain here is all real numbers. Therefore, on my interval of all real numbers, I'm good to go. I don't have to worry about any infinite discontinuities because there are none on this function. I know I just talked fast, but did that make sense to you? Are you sure? There's nothing that makes this 0 or negative. Therefore, if this is always positive, it's being squared, so no problem, it's positive. If this is always positive and I add 1 to it, it's still always positive. It can't ever be 0. Can't ever give me any problems. This is always defined. They're both always defined, so my entire rational function is always defined for an entire interval. Now the problem is that, what's the problem here? What's our problem? Yeah, it's this idea of, oh my gosh, we've got this double infinite interval where I'm not going from negative infinity to a number like 0. I'm not going from 0 to a number like infinity. I'm going from negative infinity to infinity. So What in the world are we going to do?
Split these two
Split it.
intervals.
Yeah. You know what we're going to do is instead of thinking of this as one big integral, let's think of it from negative infinity to, I don't care what number you pick. It's going to be the same, whatever you want to pick. Now I'm probably going to pick the easiest number I can think of to plug in. I'm going to pick 0, because 0 for me would be the easiest number to plug in. You guys know, hopefully from your Calculus 1 class, whenever you took it, that you can actually separate integrals like that. Start from wherever your a is, introduce some intermediate number, c, and then go from that number c to where your ending value is, b. So instead of from a to b, we go from, hey, a to c, and then again from c to b, and we add those integrals together. That's legal to do. As long as you have no problems in between there, that's legal to do. Quick head nod if you're okay with that one. Hey, have we seen stuff like this?
Yep.
Have we seen stuff like this?
Yep.
Can you guys do the next step for me? Write out what you would do. Change these into our limits for us, okay? Remember that lower bounds typically change to a's, upper bounds typically change to b's, so go for it. What is nice about this, though, is that we don't have to do the integral twice. Since we're just rewriting the same thing, our integrand right there hasn't really changed. We'll just do the same idea for both of these integrals at one time. So here's what I'm asking you to do. I'm asking you to firstly understand that when I have this type of integral, where it goes from negative infinity to infinity, you do have to do this with two integrals here. You have to separate it. So we have to have at least some solid bound in between there. Call it 0, call it 1, whatever you want. 0 is going to be easier to plug in. Remember that we do have to evaluate these sort of things, right? So we're going to have to plug in this number twice. 0 is going to be easier to plug in than negative 7 or something like that. You will oddly get the same answer out of that, but it's going to be easier to plug in if you have a 0. So we'll have, instead of going from negative infinity to 0, what's my bounds of integration going to change to?
A to 0.
Now I'm going to define it, limit as
A approaches infinity.
perfect. The inside of my integral, my integrand is not changed. Plus, what's the next thing I'm going to write? As
B approaches infinity.
good. Well, if I've called b positive infinity,
From 0 to 0.
0 doesn't change with infinity. I'm going to call that b. E to the x over 1 plus 2.
E to x.
That's not right. E to the 2x. Okay, quick show of hands if you feel okay with this idea. Just a combination of two ideas that we've had before. And here's the nice part. Once you've done this, I don't want you to do each of these integrals independent of each other. Understand that they're exactly the same. You guys get it? So off to the side, I'm not even going to worry about the a to the 0. I don't care. I'm not going to worry about the 0 to b. I don't care about that. I'm going to just do the integral of e to the x over 1 plus e to the 2x. Let's just do that. Take this idea and run with it afterwards. And then we'll evaluate whatever we get twice, from a to 0 and then from 0 to b. Do you understand that idea? So just do the integral off to the side. Now, hopefully, you can do this integral. Let's walk through it. Is it a substitution?
Yeah.
If you say no, okay. If you say yes, explain that to me.
U equals e to the x.
U equals e to, oh my gosh. Someone's good at substitution. True?
Yes.
Hey, let's be smart about this. Don't jump to a conclusion of, I don't know how to do it. Rewrite it. Think about these things. Think of, can you find a derivative somewhere in your problem? If you can, then you have a substitution here. So e to the x, not a problem. E to the 2x? Now, let's think about that as e to the x squared. If that's the case, a substitution of u equals e to the x, man, that works nice. du equals e to the x dx, the derivative of e to the x is e to the x. Check this out. Here's e to the x dx, here's du. It's right there. You guys follow me on this one? Okay, so integral that looks really hard right now, not so hard. Tell me what's going to be in the integral. Tell me.
1 over 1.
1. Okay, so this goes away. This is basically, you can write du even if you want to. I'll show you that. You can write du because e to the x dx is du. E to the x dx is du. Over what?
1 plus u squared.
Now, if you don't like the du being there, okay, call it a 1. Put the du over here. That's no big deal. I just want to make sure that you are okay doing our substitution. E to the 2x is e to the x quantity squared, and then doing u equals e to the x. Hey, no problem. This is 1 plus u squared. Du equals e to the x dx. We got a 1 du. Show of hands if you're okay with that one. Now, you've got a couple options here. You can do this the hard way, or you can do this integration table way. The hard way would be a trig sub. The hard way would be, and this would be just fine if you want to do this. Remember doing this? Even though you don't have a square root, you can put one in there. You do square root of this whole thing squared. You would have square root of 1 plus u squared. You'd have u, and you'd have 1. You would have tan theta equals u. Does that make sense? You do it that way. Or you could recognize that this right here is actually in your integration table. Now, when we're doing when we're doing integrals, the first thing we should be looking for is our integration table, right? We shouldn't make things harder than they have to be. We should try substitutions and integration table first. Well, if this is in our integration table, that's brilliant. How much is it? 10 Tanverse.
Inverse.
Made up a new word. Tanverse. Tangent inverse of u. Yeah, absolutely. That's exactly what that is. Now, let's not make a mistake I did before. By the way, would you guys know how to finish it off if you did the triangle? Let's say you didn't see this on your test. Could you do that?
Yes.
Sure, you know trig sub. Tan theta equals u. Du equals secant squared theta d theta. You'd have a little bit of work to do here, but what you'd end up getting is a secant squared theta over secant squared theta. You get 1. The integral of 1 is theta. Theta equals tan inverse of u. Bam, it's right there. It's exactly the same thing that we would get. So, tan inverse u, what's the next thing I'm going to do?
Substitute.
Very good. So, if I substitute, I get tan inverse, tan inverse of what? Perfect. Tan inverse of u, no. Tan inverse of e to the x. Show of hands if you're okay with that so far. Now, I'm going to rewrite this because I want to be a little bit more clear than what I'm being here. So, do you have any questions on this side?
No.
All right. I'm going to show you exactly what's going on with this thing here. So, what we ended up getting was these two integrals, and then we changed them to, okay, some definite integrals so that we can actually evaluate them, but we made our limits so that these bounds go to negative infinity and positive infinity respectively. So I'm going to rewrite this piece, then we're going to look at what happens in conjunction with that. So we had a limit as a approached negative infinity, the integral from a to 0, e to the x, 1 plus e to the 2x dx, big plus, limit as b approaches positive infinity, 0 to b of the same integrand. You guys okay with that so far? Now, we've already done the integral of e to the x over 1 plus e to the 2x. How much did this integral give us? So let's just change those parts. So if I know that the integral of e to the x over 1 plus e to the 2x is actually tan inverse of e to the x, which it is, can you tell me where I'll be evaluating this thing from?
Theta 0.
Sure. Is that pretty straightforward to you guys? To me, it makes perfect sense. I want to make sure it makes perfect sense to you. So we say, hey, this integral is this thing. Therefore, if I want to evaluate this integral from a to 0, I just evaluate this thing from a to 0. Now, I can't forget what?
The limit.
The plus, yes, but I also can't forget this, this limit. Plus, now, I get the same integral, which is why I've only had to do it once. It's silly if you do it twice. It's the same thing. This integral is also tan inverse of e to the x. I'm going to evaluate that from where to where, please? And I'm not going to forget there's only one right answer here. Limit. As b approaches infinity. Okay, what I want to know is, can you make the jump from doing our integral here to evaluate our integrals here? Show hands if you can make the jump. Okay, what do we do now? Plug them in. So, are we still going to have limits?
Yes.
Right now?
Yes.
Yes.
Yeah.
Have you evaluated the limit yet?
No.
No. Right now what we're doing is look. If I didn't have this limit, I'd still have to evaluate, wouldn't I? Because you haven't done the limit yet. So I'd still be plugging numbers in. So I'd have tan inverse of e to, what comes first, the a or the 0?
Zero.
The 0 comes first.
Upper
Minus
bounds always come first.
tan inverse of, that's very common for people to make that mistake, it really is. They go, oh, well, 0 always comes, no. The top bound, your b always gets evaluated first, and then you do your lower bound. Show of hands if you're okay with that one, are you sure? Okay, so here's one. Big plus limit as b approaches infinity. Tan inverse, let's try this again. Tan inverse of e to that, would it be 0 first or b first?
B.
Minus tan inverse of e to the 0. Now, are you guys okay with that one?
Yep.
Notice why we still have our limits?
Yeah.
Have you let a go to negative infinity yet?
No.
That's why you still have your limit. Now we get to let a go to negative infinity, we let b go to positive infinity. So we're going to stop writing limits right now. Let's think about this. How much is e to the 0? Hello?
1.
So this is 1. How much is e to the a as a approaches negative infinity?
0.
Very good. This is 0. As a goes to negative infinity, e to the a, this is e to the negative infinity. E to the x goes like this. So as negative infinity, we're going to 0. How about e to the b as b goes to infinity? How much is that going to be?
Infinity.
Very good. E to the infinity is infinity. How about e to the 0 again? So now that I let these go to their appropriate places, I stopped writing the limit. This was evaluating limit, saying, hey, look at that. E to the a, as a goes to negative infinity, that's 0. And this one's going to be infinity. So we have tan inverse of 1 minus tan inverse of 0 plus tan inverse of infinity. That looks a little weird to write, but we'll write it. Minus tan inverse of 1. Now, we got to be good at tan inverse. Let's see what happens. We're almost done with this thing. How much is tan inverse of 1?
Pi over 4.
Very good. So this piece, pi over 4, says tan of pi over 4 gives you 1, therefore tan inverse of 1 is pi over 4. How about tan inverse of 0?
0.
Pi over
0. Tangent of 0 gives you 0, therefore tan inverse of 0 gives you 0. Plus, how much, oh, this is an important one. How much is tan inverse of infinity? So basically, tangent of what value will give you infinity?
Pi over 2.
Pi over 2 will. Remember, tangent looks like this at pi over 2? That makes sense? So if tangent of pi over 2 is asymptotic, then we have a infinity. So therefore, tan inverse of infinity is pi over 2. It's a little weird because we can't actually plug in infinity, but we think of it like that. We think of, how can I get really close to infinity with a tan inverse? It's pi over 2. Minus, we already did this one, it's pi over 4. What's our final answer? What floors me, what's really cool, is that we have this function, right, with e to the x in there. E to the x over 1 plus e to the 2x, and somehow we get a pi over 2 out of that thing as a solid area. Isn't that kind of cool?
Yeah.
Show of hands if that made sense to you. Good deal. All right, so the last little bit that we've got to cover in this section is, instead of an infinite interval, we got to find out what happens with an infinite discontinuity. What that means is that instead of going from like negative infinity to a number, or number to infinity, or even, remember the last one we had, negative infinity to positive infinity, somewhere within our interval, whatever it is, our function's not bounded. What that means is that we're going to infinity or negative infinity along the y-axis. So basically, we just have an asymptote somewhere along the interval on which we're trying to integrate. Do you guys see the difference in the idea?
Yeah.
Infinite intervals go this way for infinity. Infinite discontinuities go this way to infinity. The function is actually going to infinity. Let me give you an example, and it's going to clear everything up. So, first example. Let's say I want to go from 0 to 9, find the area of the following function from 0 to 9. Now, right there, is that an infinite interval or a finite interval?
Fine.
Sure, that's great. So we don't have to worry about limit of b going to infinity or a going to negative infinity. We're not worried about that. However, remember the first thing I told you to check when you're talking about your definite integrals is, well, look at your bounds of integration and see if your function is defined for that entire interval. Is it defined for our entire interval?
No.
No. In fact, what's happening here with this function is this thing looks, a sketch here, looks kind of like this. Where as we go towards infinity, yeah, cool, we're going to get, you know, smaller and smaller values because we have a fraction over a number that's growing. Even though it's a square root, it's still a growing denominator. Does that make sense to you? However, as we get towards 0, what's happening as we get towards 0? It's going up. It's going towards infinity. Because when we're dividing by smaller and smaller numbers, we're getting this, oh wait, well we got an undefined zone here. And that's an issue. So as we get closer to 0, we have this issue. We have what's called an infinite discontinuity. It's not continuous. It's going towards infinity. The function is not bounded. Show of hands, feel okay with this one. Okay. Now, on the left side of 0, well, we have nothing because we can't even plug in negatives because we got a square root. So this is basically what our graph looks like. You got it?
Yeah.
So here's our idea. Instead of going from 0 to 9, what's the problem here? Is it the 0 or is it the 9 or is it somewhere between there?
0.
It's the 0. The 0 is the problem. So, tell you what. We're going to use a very similar idea to what we did last time. Instead of going from 0 to 9, maybe we'll go from, I'm sorry, what was the problem again? 0 is the problem or 9 is the problem?
0.
We'll go from C to 9. And we'll make C some intermediate value. Tell me something. Hey, you ready? Tell me something. If this was a number like 1, could you integrate this thing very easily? Piece of cake. If it was like 0.01, you could still do it. 0.0001, you could still do it. 0, not so much. We're going to have a different idea. So it's really similar to the idea of, well, we can't actually plug in infinity, but we can plug in a number, right? And then let that number go to infinity with a limit. So the idea here is, all right, well, let's call it not 0, but C. Now, the question is, what do we want to happen, after we're done with this thing, what do we want to happen to our C? Where is our C supposed to go? Okay, our C, so we want our C to approach 0. Yeah, that's right, we want C to approach 0. Now, there's a problem with this. And this is why we talked about where the function is defined to begin with. Is there any function on the left-hand side of our 0? So what this says, if you remember anything about limits, what approaches 0 means is that the function does this from both sides. Remember that? We have to make this not a both-sided limit, but a one-sided limit. So we're going to have to approach 0 from a specific side.
The right side.
From the right side. So would you use a plus or minus?
Plus.
Good. What we want is, let me recap this real quick so we understand everything about it, and then I'm going to give you the definition for it, and we're good to go. The idea is, well, you know what? The interval's finite, that's fantastic, but our function's not defined for the whole thing. We have an infinite discontinuity. Wherever that happens, listening? Wherever that happens, change it to a C. What we're saying is that, okay, I can't define the 0 here, it's undefined. So let's call it C, that way I can even do my integral. We're basically changing this to a definite integral right now from a number to 9, no problem. Can't you do a definite integral from a number to 9? We just talked about how we could. After we're all done, then we'll say, well, what do we want to happen to our C? What happens there?
Approaches 0.
We don't want the C to be here, we want our C to be there. We're going to let that C goes to 0 from the right-hand side. This is the idea. Show of hands feel okay with the idea. All right, so basically this is where we get our limit again. So we'll go, all right, fantastic. I can do an integral from C to 9. I just have to let the C approach 0 from the right-hand side of the same function. So we're saying 0 to 9, no. We'll go C to 9. That's a definite integral. Fundamental theorem of calculus says we can evaluate definite integrals. That's why we're doing this right now. So we go, okay, c to 9. Cool deal. Do the integral, plug in 9, plug in c, subtract the two values, and then at the very end go, wait a minute, let's trick it again. Let's say, no, I don't want just c, a finite number. I want to say that thing's going to go to 0 from the right-hand side. It's going to get closer and closer and closer and closer and closer. Quick head nod if you're okay with the idea. Now it's just a matter of evaluating it. It's going to be a limit again. Can you guys evaluate this integral? What would you do with this?
Make it a 1/2.
Yeah. So c goes to 0 from the right. Remember, we still have to write that. C to 9. By the way, if you didn't catch where the c is coming from, a is typically called a lower limit. B is typically called a lower bound. B is your upper bound. So if we had negative infinity, we call that our A. Our positive infinity would be our B. Anywhere in between these two numbers is typically a C. So that's where the C is coming from. Okay, so y'all said that this should be x to the, what am I going to do here? X to the what?
Negative 1/2.
Oh wait, I'm sorry. 1/2 or negative 1/2?
Negative.
1/2.
Good. I'd move this up. That'd be x to the negative 1/2 dx. Cool deal. Let's keep going. So this will be our limit as c approaches 0 from the right. Let's go ahead, let's do our integral. What's the integral of x to the negative 1/2? Tell me that one. Okay, x to the 1/2, I like it.
2.
Over 1/2. So basically 2. So if you guys feel okay with that integral. I'm going to kind of have to warn you now, I'm going to go fast through a lot of these integrals because the idea is no longer, hey, can we do integrals? It's let's look at how to do these improper integrals. Does that make sense to you? So actual integration, we're going to go a little bit quicker. Now, do I still have an integration symbol here? You've already done the integral. So all we're doing now is evaluating. Where are we evaluating from?
9 to C.
Okay, which way? 9 to C or C to 9?
C to 9.
Which one do we plug in first? So this will be the limit as c approaches 0 from the right-hand side, 2 square root of 9 minus 2 square root of c. Still okay so far? Let's talk about these things. Let's talk about what happens as c approaches 0. What's going to happen to this part? How much is that going to go to?
6.
Sure, this is 3, that's 2, so we're going to get 6. Notice how we're stopping writing the limit once we evaluate the limit, but before that we have to have it every single time. Now, what happens to the square root of c as c approaches 0? Notice we don't have a two-sided limit here, which is why we had to go from the right-hand side only. It doesn't exist from both sides. So just think about what happens. What happens to a square root of a number as that number gets really, really close to 0? It gets really close to 0. Does that make sense to you?
Mm-hmm.
If you plugged in 0, you'd get 0. So we'd have minus 0. Therefore, what's really this is so cool. I don't know why it's so cool to me, but it's so cool to me. It says that, what's an integral even mean? So this is a definite integral, right? Between 0 and 9 of something that's not even defined as 0. Yet what happens is that if I have the area, because of this, because of our limit idea, the area under this curve from 0 to 9 is equal to, very cool idea. Very cool. Show of hands if you feel all right with this. So there's a few scenarios I want to discuss with you. Let's say that we have, so for a discontinuity at B, for discontinuity at A, or for a discontinuity at some intermediate value, C. So let's say we have some function, and there's going to be a discontinuity here, an infinite discontinuity at B. So our function is defined at A, no problem. It's going to do something, I don't know what it's going to do, but somewhere around B, there's going to be an asymptote. Do you guys see what I'm talking about, the infinite discontinuity at B? Hello, yes, no? I don't care what happens past it. My interval is going to be from A to B. I don't care what happens before it. My interval is going to be from A to B. Does that make sense to you? So if I tried to integrate from a to b of some function, then the idea is, well, let's look for the problem area. Let's look at what's wrong with our integral, what's making it improper. Now clearly, hopefully it's clear to you, my integral is finite. It's going from a to b. It's not an infinite idea, so I don't have to go to positive infinity or negative infinity. It's not a problem. But what is a problem is that while a is defined, b is not. So my discontinuity would be where, a or b? So wherever that discontinuity is, that's what we're going to call C, or whatever you want to do. So you can call it any letter you want. We typically use C because it's going to be an intermediate value between A and B. Does that make sense to you? So for us, we go, all right, well, awesome. So we'll have, I'm sorry, which one would we change here? Would we change A or B?
B.
That would become a C. So we'd say, no, not B. Let's make some point C, some intermediate value. And then where are we going to let C go to? We're going to, not infinity, because I'm not going to infinity anymore. I'm going to go to B. So the limit would be C approaches B. Now think carefully here. So here's the idea one more time if I didn't cover this well enough for you. The idea is you're going to have a problem with an infinite discontinuity. It will either be at A or at B or somewhere between there. I'll show you that one last. If it's at one of your endpoints of your interval, A or B, well then define that endpoint as some intermediate value, C. So we go, no, we can't go all the way to there. So let's go to here. Let's go to C, not B. Does that make sense? Do our integral, because now it's a definite integral that's defined from A to C. You got it? After that we go, all right, well, where does the C really want to go? C wants to go this way a little bit. C wants to go this way a little bit till it hits B. Now, from which way? From the left or from the right? From the left. That would be the idea. I want to show of hands to see if you're okay with this one. Now let's reverse it. Let's say that we have some function that has a discontinuity at A, but is defined at B. Can we do it the way it is? Well, no. We have an infinite discontinuity. The interval is great. It's from A to B. Not a big deal. So if we had an integral that says, I want you to integrate from A to B of whatever this function is. Where is our problem here? Is our problem at A or is our problem at B?
B. I mean A, yeah.
It's at A. B is fine, right? B is defined. We're good to go. So what we go is, well, tell you what, I don't really care about going to B. That's good to know, but I can't start at A. If I can't start at A because it's not defined, where am I going to start?
C.
Some intermediate value C. So my B would stay the same, but my A would become a C. What that lets us do, again, hopefully for the last time, that gives us a definite integral that we can actually evaluate. It says, now you're going from a finite number to a finite number that you can actually plug into your integral when after you've already evaluated. That's great. We go, okay, plug in the B, plug in the C, subtract them, good to go. Calculus tells us we can do that. We can subtract that evaluation when we plug in B and then subtract off when we plug in C in this case. Now, the problem is, well, I'm not really starting at C. I want to start where? I want to start at A. So, yeah, this integral says from C to B, but now this limit can take the C and move it which way?
To the right.
To the, okay, so let's just say to somewhere. To where?
To A.
To A.
From the right side.
From the right side. That's right. That's actually the first example that we had. That's right here. That said, okay, I can't start at 0, but I can start at C. Now, at the very end, we go, okay, look at that. From C to 9 actually lets you evaluate it. Plug in the 9, plug in the C. That's great. That's what definite integrals are all about. Then it says, well, I want that C to not start here. I want it to start really close to here. And that's what this limit idea says. I want the C to start really close to here. So towards 0 from the right-hand side, that's what this is. Show of hands feel okay with that one. Now, there's one situation we haven't covered. What's the situation we haven't covered?
Where there's a hole right in the middle.
Holes I don't care about, because that's why they're called removable discontinuities. They're not going to affect us. It's still bounded, correct? So if we have a hole, we can plug it with a single point. Does a point have any width to it? This is going to blow your mind. If a point has no width to it, then if I'm missing a point on my line, so a hole basically, since a point has no width, it can't possibly have an area under that point. Does that make sense? This area is width times height. If it has no width, I don't care how high it is, 0 times anything is still 0. So for that reason, if I have a removable discontinuity, that does not affect the area under the curve. Those points have no width. Crazy, right? What will blow your mind is you can have an infinite number of those on your line and still get an area. What? Anyway, it's different class. different class. Discontinuity at C. So what happens if it's not, did I just completely blow your mind like a mind grenade? Do you see what I'm talking about? How that one point doesn't affect the area?
Yeah.
That's so neato, because there's no width. So therefore we don't care about the holes. We care when it's not bounded, right? Because that's a problem. We need to define that a little bit better. So it's not here anymore, it's not here anymore, it's somewhere in the middle. So here's our A, where we have something defined. Here's our B, where our function would be defined. But somewhere in here, we've got a problem. Oh, did I say infinite number of holes? I think I might have meant finite. I'm not sure. I don't remember anymore. Could be a finite number of holes. Whatever.
Whoopsie.
That would be just a little bit of a problem there if I don't know that exact thing. Well, what's the issue here? Are we defined at our endpoints of our interval, at our endpoints, A and B? Are we defined?
Yes.
So then our infinite discontinuity doesn't happen here, and it doesn't happen here. It actually happens right in the middle. Whenever you get this case, this is the worst case scenario. This one's kind of nice, because you just go, okay, it's one limit. Does that make sense to you? One limit, because we have one discontinuity from one direction. Here, no problem. One limit, one discontinuity from one direction. Here, one discontinuity, but it's from two directions. So whenever you have your infinite discontinuity between your bounds of integration, the A's fine, the B's fine. Somewhere in the middle we have a problem. So somewhere in the middle we'd say, okay, where would we go? Where would we start from if I want to do this? I'd start at A. Where's my problem at?
C.
Yeah, I'd have it at C. I'd have to split that up. Then I have another integral starting from where?
C from C.
And go into
D.
after you do this, so basically here's the idea. If you have it at one of your end points of your interval, not a problem. Just call it from A to C or from C to B respectively, and let that C go to the appropriate number. If it's in the middle, you have to break that up. So the starting point to where C is, then C to where the ending point is, where your ending interval is, and then you do basically the above. So basically, do you guys see that this idea is a combination of these two ideas? We'd get one of these, and we'd get one of these. Specifically, this integral is this one. This integral is this one, and you do exactly the same thing. Make sense? Are you sure? You guys want to try a couple of them? Okay, probably. Let's do some. Any questions?
What if it doesn't approach infinity on both sides, only one?
You can still
It
try.
has a point and then it comes down from infinity.
What do you, oh, like a piecewise defined function like this one?
Yeah.
That'd be great, because this integral is defined. So this would be like easy. Okay, you say, hey, A to C, no problem. But then this side, you still have to split it up, because it's not continuous. You have an infinite discontinuity, hence the not continuity part, okay? So this would be good. This part, you say, well, I got to do this one here. That's a good question.
So you just would skip the limit on one.
You wouldn't have to do it for the left side. That'd be easy, because it's actually defined. That's a good question. Any other questions?
What would the limits look like for the A to C and C to B?
It's easier to show you with actual numbers, but what you do is you call this intermediate point D. And you say a limit as D approaches C from the left. You'd say a limit as maybe E. as e approaches c from the right. So you have to have, this is why I don't want to show you that many letters, because like, what in the world are you talking about here? But you go from a to some number d, okay? You do your definite integral, and then you let d go to c, your undefined point, from the left-hand side. Here, you define some intermediate point e. You've already used c and d, so e. Then you do your definite integral from e to b. After that, you let e go to c from the right-hand side. Did you guys follow that? Same idea, it works easier with numbers because I don't have all these letters floating around. Okay, so let's actually get to the nuts and bolts of this thing. You know, one of the most important things we can do as integrators of these improper integrals is determine what we're talking about, whether we have an infinite interval or whether we have an infinite discontinuity. Which in this case do we have, an infinite interval or an infinite discontinuity? Interval's great. We're going from 1 to 4. That's a definite interval. It's finite. But within that 1 to 4, we've got a problem. So you have to define all the problems you have, and there can be several of them. You could have a problem at an endpoint. You could have a problem at both endpoints. You could have a problem at both endpoints and somewhere in the middle, or several places in the middle. Now, of course, right now we're going to keep it kind of easy, right? There's going to be like one problem. But you could have many, many different problems. Does that make sense to you? So everywhere your denominator is 0, that's an infinite discontinuity, provided you can't simplify out provided it's not a whole, basically. That you would get from calculus 1, the difference between wholes and asymptotes. If you had me, you should know that exactly what the difference is between wholes, removable discontinuities, and asymptotes. So in our case, where is our problem at?
4.
It's not at 1. 1's great. I can plug it in. It's not 0. 2, 3, cool. 4, that's a problem. So what we're going to do is we're going to say, well, you know what? If it's not defined at 4, let's make it be defined somewhere at some intermediate point C. Are you guys with me on this one? That's, which case is this? Is this the case for 1, 2, or 3? Which case do we have?
1.
We have 1. We have this one. It's fine. It's defined at A. It's not defined at B. It's defined at 1. It's not defined at 4. So we're going to call this some point right before the B. Right before the 4, we're going to call it C. Maybe it's 3.9999999 forever. I don't know what it is. We're going to call it C. And we're going to have exactly the same function. We just have to say what's happening on my interval. So we have to say where C is going. So how do we say where C is going? What are we going to use?
Limit.
Yeah, limit is the way we say where a number's going. A limit as C approaches where?
4.
It's always going to be this number, or some number in between there. It's always going to be a number. So it's not going to be a random letter anymore, okay? We're defining what's happening to the C. Now, you got to be good at this. Is this C 4 from the right or 4 from the left?
Left.
From the left. So let's see if it matches up. C is going to the top number from the left. C is going to the top number from the left. Hey, that looks exactly right. Can you do that integral? It should be pretty easy. What would you use in order to solve this integral?
Here, substitution.
Yeah, what would the u be? du equals negative dx, or negative du equals dx. Again, I'm going to go kind of quick on this, but do not neglect your substitutions, okay? Your signs are important. You guys see where the negative's coming from on that one?
Yeah.
That's important. Okay, so we have a limit as C approaches 4 from the left of the integral from 1 to C, u to the negative 2/3 times negative du. Tell me what I can do here. Okay, you can actually pull it all the way out front if you want to. You can pull it in front of the integral, it doesn't really matter. U to the negative 2/3 du. Can you all integrate u to the negative 2/3?
Yes.
How do you do that?
3u to the 1/3.
Okay, so we have our negative. We add 1, we get 1/3 divided by what?
1/3.
So divided by 1/3. So this would be 1/3 divided by 1/3.
times 3.
U to the 1/3 divided by 1/3. No more integral. We've already done the integral. What's the 1/3 change to? 3. Now, we can evaluate right now from 1 to C, or you could pull your -3 all the way up front. I might choose to do that just to show you that it's possible. So from here, I can pull that -3 out in front of my limit and do U to the 1/3 from 1 to C. Now, there's a big issue right now with plugging in the values. What's the problem?
Changing bounds.
We didn't change bounds. So if you didn't change bounds, instead of plugging into U, what do you do first? We gotta take this substitution and put it back. So we're gonna have to do -3 times the limit as C approaches -4. Oh, sorry, 4 from the 4 from the left hand side of what's it gonna look like?
4 minus x to the
1/3.
Okay, so 10, 20-second recap. Here we go. We first identify what type of problem we have, whether it's an infinite interval, whether it's an infinite discontinuity, maybe both of them. Look for all your problems. Here we're defined, we're good to go. Here we're not defined at this number, at that endpoint of your interval. We call that some intermediate value C. We say, hey, where's the C going? Well, it's going to go to 4 from the left-hand side. We don't care about the right-hand side. That function's not even there. We don't care. We're going to evaluate our integral any way that we can. We have lots of techniques to do that. Get all the way down to here, and then, oh my gosh, well, if you use a U substitution before you evaluate definite integral, you definitely better plug back in your U. So we have a 4 minus x to the 1/3. Now we get to evaluate. So we've got -3, let's not forget that. A limit as C approaches 4 from the left. What goes in first, the C or the 1?
The C.
4 minus C to the 1/3 minus 4 minus 1 to the 1/3. This is the point where you can start to evaluate your limit. Notice we've had to write limit every single time until we get right down to here because we haven't thought about what's happening as C is approaching 4 yet. So this right here, look at, this is your definite integral. This is evaluated on your definite integral. Does that make sense? This is where you say, okay, now what was happening? C really wasn't just the number I wanted to stop at. C was something I wanted to go to 4 from the left-hand side. Does that make sense to you? So let's see about, no pun intended. Let's see about the C. What's happening to the C? It's getting really close to 4. Really close to 4. What's 4 minus something really, and when I mean really close, I mean it gets to 4, practically speaking. How much is that?
0.
So this thing's going to go to 0. Since C is going to 4 from the left-hand side, this thing is getting really close to 0. 0 to the 1/3 is still 0. So we're going to have, don't forget about this -3, it's still there. So we have -3 times, this is 0, minus, how much is this going to be?
cube root of 4.
Cube root of 3. Altogether, we have 3 cube root 3. This part should be pretty easy. Show of hands if you feel okay with this stuff. Can we move on just a little bit? Okay. So moving right along. Questions? All gone already. Have I taught you what the integral of ln x is? Have we done that in this class
1
before?
over x, right?
Oh no, it's the integral of 1 over x, not the derivative of ln x. The integral of ln x. Have we done that? I think we've done it once.
Yeah.
Yes.
Sorry. U times v minus the integral of v du. What am I doing up here? Magic?
Partial.
Which is magic?
I mean, integration by
Integration
parts.
by parts. U, v minus integral of v du. This is 1. You know, I never miss those C's. Sometimes I do the wrong thing, but I never miss those C's. There we go. We get x ln x minus x. Do you guys see where the x is coming from? It's just basic integration by parts. I know we've done it at least one time before, but what that means is that if I wanted to evaluate this limit from, oh, where do I want to go? 0 to 1 of ln x dx. Now I can use this formula, basically. I wouldn't have a c, but now I can use that. So whenever you see the integral of ln x, if you want to memorize this, that's fine. Integral of ln x is, by integration by parts, x ln x minus x. Show of hands feel okay with the integral. I know I did it fast, but we've done it one time before. So let's look at the integral from, this is our real example, okay? Let's look at the integral from 0 to 1 of ln x. Firstly, is this an infinite interval or is it an infinite discontinuity?
Infinite discontinuity.
Very good. Where is the discontinuity? 0, 1, or somewhere between?
0.
1.
1.
What's ln of 1?
0.
Then it's defined. Oops. What's ln of 0?
Tricky.
Error.
Syntax error. Syntax.
My calculator won't do it. I don't know. Do you know what ln x looks like? You better.
Yes.
It's the inverse of e to the x. So if e to the x looks like this, ln x looks like that. Now, you all think that it's undefined at 1 because when you plug in 1, you get 0. That's not something that's undefined. It's actually defined. But the definition is ln of 1 is 0. That's not a problem.
It's at 0.
What our problem is at 0 from the right-hand side. That's our problem. ln isn't even defined on this side. Not even defined at all. Okay? So, our problem here is, well, your problem here. I don't got a problem here. I'm good. All right? But it's not at 1. 1's good. We're good at 1. We're not good at 0. So, help me out with it. What do I call the 0? What am I going to make it?
C.
Let's make it C. Yeah, I'm not making it A because I'm not letting this number go anywhere. I'm not letting it go to infinity or anything. I'm calling it C because I have a number between 0 and 1 right now. Does that make sense? It's between 0 and 1. Now, where do I want that C to go?
0.
From the right. I mean, correct. And a limit lets us do that. Well, I made a really big integral, didn't I? I want to make sure you know that's an integral. Quick show of hands, feel okay with that one so far? So 1's good. Man, it'd be kind of worst case scenario to pick the wrong thing, right? And go, oh, this is completely undefined at 1. No, it's not. It's great at 1. It's not great at 0 because it goes to negative infinity. That's a problem. So we say, hey, 0 to 1, no. Call it a number. C to 1, somewhere just before 0 as we're going from the right. Just before 0. Do your integral because we have a definite integral now. After that, you go, okay, cool. After you've done your definite integral, where do we want the C to go? Now we want the C to go to 0 from the right-hand side. This is the idea. Did you get the idea? Are you sure you get the idea?
Yes.
All right, so now that I've shown you how to do this integral, no problem. You got a limit. As C approaches 0 from the right, the integral of ln x is x ln x minus x. We do not need the plus c because it's a definite integral. Where's my bounds of integration? From where to where?
C to 1.
Which one do I plug in first?
1.
Very good. So this will be a limit as c approaches 0 from the right of c times ln c minus c.
1 first.
I was just checking to see if you were paying attention. I didn't even write the c's. I wrote the x for some reason, I don't know why. 1 ln 1 minus 1. I even asked you that question, didn't I? Silly old Leonard. Minus, okay, now we'll have c ln c minus c. Can you see why this is correct? Anyway, show of hands if you feel all right with that so far. Now let's start simplifying this thing. What happens with ln1?
0.
That's 0. What happens with, oh goodness gracious, you know what? We're going to do one more thing with this. So we know that's 0. I'm going to rewrite this just a little bit. I'm going to write this as limit as c approaches 0 from the right. Let's do this. Let's do -1 minus c ln c plus c. Are we okay with that so far? Hello, yes, no?
Yes.
Okay, now, you can't make up your own math on these things. Some are going to be easy little parts, some are not going to be so easy. You have to do some things with it. So let's look at this. What's the limit of -1?
-1.
Easy. What's the limit of c as c approaches 0 from the right?
0.
That's 0. This one? Oh. This is 0 times negative infinity. That's an indeterminate form of 0 times infinity. We'll have to rewrite that one. You guys follow me on that one? You can't do 0 times... You should know that ln of c as c approaches 0 from the right goes like this to negative infinity. You can't do 0 times infinity and know what that is without doing this. Okay, you've got to actually go through it. Am I getting through to you a little bit? Okay, you've got to do the indeterminate forms like we've been practicing. That's why we did them, is to get here. So we're going to have, this is still -1. This goes to 0. So I'll have -1 minus the limit as c approaches 0 from the right of c ln c, and then, well, plus 0. That's gone. So really, I just need to focus on this thing. I'm going to take it off to the side here real quick. Use a different color here. The limit as c approaches 0 from the right. If you remember anything about indeterminate forms, like 0 times infinities, or 0s to the whatever, we're trying to make a fraction out of it, of 0 over 0, or infinity over infinity. Explain to me why we're trying to make a fraction out of it.
To do L'Hopital.
Very good. So, never want to move ln to the bottom. We found that out when we, remember doing e to the ln of the bunch of junk? We never move the ln, we always move the other thing. So this, you'd leave this as ln c over 1 over c. Which was the idea.
C the -1, would that work?
You can, but you're going to be doing a derivative right now.
Oh, I know.
Now, let's identify this. What is this as we go from, this is infinity, this is negative infinity. As we get really close to 0, this thing's also infinity. If this is infinity over infinity, we can use,
L'Hopital.
so this was infinity over infinity. A weird infinity. This was infinity over infinity. So with a L'Hopital's rule, I'm going to do L'Hopital's really quick. We get 1 over c over -1 over c squared. Derivative of ln c is 1 over c. Derivative of 1 over c is -1 over c squared. Are you guys okay with that one? Can you simplify that? Of course you can. Let's see. It's going to be negative. 1 over c over 1 over c squared. Reciprocate and multiply. C. We get if you simplify this, you're going to get negative c. Got it?
See?
C?
See.
C. Now, what's happening? Are we really okay with? Oh, C, can you see?
I see what you
That was
did
3
there.
different C's.
I see what you did there.
Thanks. So, what's happening to our C as C approaches 0 from the right? This thing is going to -0. Well, I don't care about -0. 0. So this whole thing is 0. And we get -1. Crazy. Quick show of hands, feel okay with that one? Are you sure? So the idea is, man, you can do all these integrals. They're pretty easy. Be careful with how you set it up. Identify where the infinite discontinuity is. That's important. If you can do that, you get your correct limits, okay? After that, man, you can't cheat at your limits. Don't make up your own math. Do them the way I showed you with indeterminate forms, okay? Really make sure that you know how to do those limits. Maybe refresh your memory on the section of indeterminate forms. So let's do two more. We'll talk about one. We'll actually do another. See if you're really with it here. We're not going to finish this, but I want to see if you understand what to do. Integral from -1 to 1 of 1 over x squared dx. Integral of -1 to 1 of 1 over x squared dx. Infinite interval? Infinite discontinuity? Neither. Both.
Neither.
Infinite interval? Infinite discontinuity. Is there a problem in our function? Where? Zero is a problem. Do you see what I'm talking about? The zero. Zero is a problem. This is what I'm talking about. You can't just blindly integrate with definite integrals. In Calculus 1 you can, because you don't cover this idea. You go, okay, I'm just going to assume I can do it. But here you can't do that. Because now, well, can you plug in 0? The goodness gracious, folks, we're going over an interval where this function is not even defined. What that means is that we have this third situation where we've got a -1 to 0 plus a 0 to 1. Show of hands if you feel okay with that idea. I'm not going to finish the problem for you. I think you can do it. Check it out. Ignore this side. Could you do this? Yeah, this would be as c approaches 0 from the left. As c approaches 0 from the right. And then you do both of them and add them together if they both exist. Thanks for the emphasis on that one. Okay, last one.
I have 84%.
Last one. Integral from 0 to infinity of that bunch of junk. Oh my gosh, one of the most important things you can do is actually identify what is going on, what is wrong with your interval, or your integral, or both of them. So what's wrong with this picture?
Infinity.
Infinity, right off the bat, it smacks you right in the face. It says, boom, got an infinity. Did that wake you up a little bit? So that's an infinite interval. We're going from 0, that's 0's great, all right? Well, 0's great as far as the interval being defined, to infinity. That's going to be a problem. We're going to have an issue there. Does that make sense? Now, there's another problem. What's the other problem? We're defined everywhere except at 0. 1, 2, 3, 4, boom, boom, all the way to infinity is perfect except for the 0. So here's how we, and you can take these ideas and run with it, okay? I'm giving you kind of the basics here. So if you had started like, you couldn't start anywhere negative, but like on example like this one, if you had other scenarios, you got to break them up to where your interval is defined and do limits for where you are not defined. Is that clear? So in our case, we're going to say, not a problem. No, but we can do this. Not a problem. But here's how to split it up. If you have an infinite interval, we're going to have somewhere where we can start at a finite number and end at an infinity. For here, for our infinite discontinuity, we're going to have somewhere where we start at 0 for sure, but we end at a finite number. So what we're going to do here is we're going to split up our integral with some intermediate value that's relatively easy to plug in. So, are you guys with me on the idea? We know that we can separate integrals as long as they're, well, continuous, or as long as we separate them and make a discontinuity with our limits now. So basically we can separate them anywhere we want to. We typically will separate at the discontinuity if one exists between our ending bounds of our interval. However, if we have no infinite discontinuities between the bounds of our interval, just pick a random number, or pick one that's easy to plug in. What number is easy to plug in between 0 and infinity? 1. Does that make sense? Add them together. Now tell me something. Now that you've broken it up, can you do this integral?
Mhm.
This is improper. It's definite interval here. It's just undefined at that point. So we could write a limit as, what number's going to change? Real quick, what number's going to change?
Zero.
To a
Hey,
One.
C.
Oh, see?
C.
Well,
Third time's the charm. Okay, now where's that C going to go? From the
Right.
From the right. Listen, if it's a left-hand bound, you're going to have to get there from the right. If it's a right-hand bound, you're going to have to get there from the left. Because there is no other side of that. Show of hands feel okay with that one. Do you guys see how this idea is the stuff that we literally just covered? It is this. All you got to do is break this thing up. So now, next one. We're going to have a limit. Okay, let's see if you remember this from last time. The one's not going to change. What's the infinity going to be?
B.
As b approaches e to the negative square root of x over square root of x. Now be smart about this. Don't do the same integral twice, 2 different times. Just do it once and use it for both cases, okay? So for us, I'm going to really rip through this thing very quickly because I have about a couple minutes left. And I'm going to assume that you know how to do this. I guess you could have made that -2. Now let's do that. So u is negative square root of x, get -1/2 x to -1/2, move over the -2 square root of x du. That is our dx. Bam, square root of x's are gone, pull out our -2. Our integral becomes -2 e to the u. So far so good? Now of course, before I start evaluating this thing, I'm going to want to make sure that I have my function in terms of x and not u.
Should be du, not dx.
Oh yeah, thanks. Yeah, thank you for that. So -2 e to the u, -2 e to the negative x. Show of hands feel okay with that one. Basic u sub. Okay, if you need to watch that again, watch it again. Now, we've got both of these pieces. So what we end up doing is, once we've done this integral, now take that idea and put it here. So we have, from this side, we've got a limit as c approaches 0 from the right. This integral is this, -2 e to the negative square root of x. It's just that we're evaluating from c to 1. Okay, I really want to make sure that you guys get this idea. Are you okay that this integral is this piece, and I'm just going from c to 1? Yes or no?
Yeah.
Are you sure? Is everybody sure on that one? That's a big deal. So we integrate once and we use it twice because we're just splitting up the same integral. Show of hands feel okay with it. Okay, fantastic. Now we're going to add on to it a limit as b goes to infinity. Well, this integral is this piece. Only on this particular integral, I'm going from 1 to b. So we evaluate. Limit as c goes to 0 from the right. Which one do we plug in first?
1.
-2 e to the negative square root of 1 minus -2 e to the negative square root of c. This minus this. So I'm doing the plus here. Do you guys see where the plus is coming from? I don't want to blow you out of the water, but I got to go quickly here on this one. So this minus a negative, that gives us a plus. You okay with that?
That's where I would have messed up.
little piece, minus a negative. I'll do it over here if that bothers you. Negative 2e to the negative square root of b minus negative 2e to the negative square root of 1. Here's what I'm talking about. This is what we did here. So when I subtract a negative, what does this become, ladies and gentlemen? Okay, now we're almost done. Tell me, what's the square root of 1?
1.
Negative 1? So this is negative 2 over e. Does that make sense to you? Negative 2 over e. Now what's happening to the c?
It's going to 0.
It's going to 0. What's the square root of 0? So look at this is getting really close to 0. You with me? Square root of 0 is negative 0 is e to the 0 is
1.
So this goes to, well, e to the negative 1. E to the negative 1 is over e. So negative 2 over e. This is 0. E to the 0 is 1. This gives us 2. You guys with me on that one? Plus. Let's go to infinity.
Square root of infinity.
0. E to the
Square root of
negative 2.
infinity.
What's my problem? This is right, right?
The square root should be 1.
Yeah, b comes first. Plug in the b, then plug in the 1. B comes first. What's the square root of infinity?
Infinity.
Still infinity. This is negative oh, think careful. Do you guys see what I'm talking about? Negative infinity? E to the negative infinity is? Thanks for the stadium yell. Okay, now how about this one? Square root of 1.
1.
Negative 1. What's e to the negative 1?
Over 2 over e.
Negative 2 over e.
What happens? What's our area?
2.
So this was this is 2. This is 0, because e to the negative infinity is 0. 0 times anything is 0. This gives us this again, bam, bam, we get, oh my goodness. This is crazy, okay? Crazy. So we do all this work
to
from
get
0,
2.
where it's not even defined, to infinity, where we're going forever, of this function, and because of our limit idea, we figure out this area under that curve is
2.
Bam. Our last little bit of section 7.6 of this section is dealing with something that's a little bit of a kind of a nice application that we can use improper integrals, use to our advantage with improper integrals. Here's the idea. Let's suppose that we know something about two functions. Specifically, we know that if we compare two functions, one is always greater than or equal to another graph on this interval, or one is always less than or equal to another graph or function on this interval. If we know that, then sometimes we can say something about the convergence or divergence of these integrals without even doing them. Did you hear that? Without even doing them. And the reason why that might be nice is because there's some integrals that we can't do. There are some non-integrable functions, so if we compare them to some that are possible, we can find out some nice things about it. Does that make sense to you? Let me give you a picture of what I'm talking about, okay? So let's say that I've got some function f of x. And I don't care what this function looks like, it's just some function. And it goes forever. And I've got some function g of x. And it goes forever. Now here's the thought process. I'm going to try. It's a very simple. What I have to write here is very simple. It's going to be like one little statement, one little statement. But I want to make sure that you guys understand the concept. That's what this class is about, right? It's understanding the concepts here. So think about this for a second. Firstly, do you see that f of x is always greater than g of x for any number that I give you from a, and let's assume this goes like this forever, okay? From a to forever. Are you guys with me? Always greater than or possibly equal to it. Let's look at it. The black line is f of x, the purple line is g of x. Is the black line above the purple line?
Yes,
Is the black line above the purple line?
yes.
How about right here? Oh, it's equal right there. Does that matter? No.
No.
It can be equal to it, that's fine. As long as it doesn't jump above it, that would be a problem. But there's always equal to it or less than it. So would you agree that f of x is always greater than or equal to g of x for any number from a to infinity? Show of hands if you understand the concept. Okay, now here's the plan. Think about what would happen for these scenarios. Let's say that we take an integral of g of x. Let me start with f of x. Let's say we take an integral of f of x from a to infinity. Remember the improper integrals that we've been doing? Watch the video from the beginning if you don't remember that. If we go on this indefinite interval from a to positive infinity, we go, okay, let's take the integral of f of x. Let's say that we can find it. So the integral of f of x from a to infinity is actually convergent. Remember convergent? Remember the word convergent? It means the area exists, the limit exists, so the area exists. So we do this and we say, oh, you know what? I can find, here's the key thing, so focus right now. I can find the area of f of x from a to infinity. You get that? Therefore, the integral of f of x from a to infinity would be called convergent. Now here's a thought. If the integral of the black line is convergent, what would that tell you about the integral of the purple line of g of x?
Convergent.
It has to be convergent. If the big one converges, this one's bounded. It's bounded by this, that's what this says. It says that f of x is the upper bound for g of x. It's bounded, so if this converges, this one has to. It's like it's squeezing it, almost like it's squeezing it down there. Does that make sense to you? So it's bound by the x-axis and by f of x. Well, if this is always above this, if this one converges, a smaller function would also have to. It's like it's getting squeezed down even more. Show of hands if you understand that one. So, that's what we're going to say here. If this integral is convergent, then so is this one. If integral from a to infinity of f of x dx is convergent, then the integral from a to infinity of g of x dx is also convergent. I really do want to make sure that makes sense to you. Do you understand that concept? So if the f of x converges, that area exists, then g of x has to. It's smaller than that. Question?
So g of x just can't go down forever, or does it have to stay above some point?
Yeah, we're going to assume that it's bounded by this, but even if it isn't, even if it's not x-axis, if this went down below it, as long as f of x is on top of it, you can still do it. Does that make sense? There's the only condition we have to have. This has to be above that. What can't happen, it can touch. That's fine. There's the difference in areas between there for the interval where they touch is 0. It just if it goes above that, that's a problem. Does that make sense to you? Okay, so now next one. Think about the backwards way. Let's say we know something about g of x. Let's say that we calculate the area of g of x, and it's divergent. So that means that we go, okay, the area under here, oh, it keeps growing without bound, or we can't find it. What would that tell you about the area of f of x, or under f of x?
We don't know. We don't know.
Is it possible for the integral of g of x to diverge and the integral of f of x to converge? No. If this one grows without bound, remember we're saying this is bigger than that. Does that make sense? If this one grows without bound and f of x is always bigger than that, how can f of x converge if g of x grows without bound? It's not convergent. So if g of x is divergent, and we know f of x is bigger than that, so g of x goes, can't do it. F of x is larger than that. Can f of x also converge? No. So if g of x diverges and f of x is bigger than g of x, then the integral of f of x also diverges. I used f of x instead of integral of f of x, but hopefully you get what I'm saying. If the area of g of x diverges, the area under f of x is bigger than that. It must also diverge. So if the integral from a to infinity of g of x dx is divergent, then the integral from a to infinity of f of x dx is also divergent. Quick show of hands if you feel okay with that. Basically it says, hey, if the big one goes somewhere to a specific number, g of x also has to do that. It's kind of squeezed between them, it's bounded. If g of x goes to infinity, then f of x also goes to infinity. That's the idea here. Sure you're okay with it? Okay, would you like to see an example? You only get one example here, because it's honestly just this idea. But here's why we would use this. So let's say that I give you an integral from 1 to infinity, 1 over x plus sine squared x dx. And again, here's why you might want to do this. Integral from 1 to infinity of 1 over x plus sine squared x dx. Is there anything that you know that will take care of that integral for you? It's not a sub, for sure, because there's no cosine anywhere to be found. It's not a sub. It's not a biparts, because you have a plus there. It's not separable by product. It is not partial fractions, because those are not polynomials. It's not a trig sub. You can't complete the square with that. And there's an x, not an x squared. No. No. There's nothing you know how to do for this integral. Some things you can't directly do. Some integrals you can't do. So, and I know that's a shock to you. Wait a minute. This is math. Math, sorry. Right here, there's nothing that we know how to do for this integral. Maybe somewhere else numerically or approximations, for sure, okay? There's other things that we can do. But here, no. We can't do anything with this in our class right now. So what in the world are we going to do? Well, the most we could say about this is whether it is convergent or whether it is divergent. That's something we could probably do here. So we're going to make a comparison to another function that we do know how to do something with. Now, we might not be able to find the actual area of this, but we can tell whether it actually goes to a number or whether it doesn't. Does that make sense to you? Whether we should spend time trying to find it or whether it's a waste of time. So here's what we're going to do. We're going to compare this to another function. Something that is going to be easy to do. Now, keep in mind that if we're going to do this, we do have to keep the bounds of integration the same from here to here, just so that we match this up. So notice that our A and our A, they match up. Perhaps we think of this. We're going to try to compare it to that. Now here's how we're going to compare it. Now where did I come up with that? Well, I'll show you in a second how I came up with that. But a lot of times when you're just learning this stuff, it's going to be given to you. It's going to say, hey, compare this function to this one. Just to get you guys in the habit of seeing how to make that comparison. Does that make sense? So it'll typically be given to you. I would say, like on one of my tests, I'd say, hey, you know what? Take this thing, compare it to this. So what am I doing here? Well, I'm getting rid of at least the sign. I'm trying to limit that. Also, I'll show you why the sign gets limited to this, and the x, I don't have to change that at all. I'll show you that in just a second, okay? But the idea is, let's try to find something that is going to contain all the time, so be bigger than this function, or all the time be smaller than this function. Let me show you. So the first thing we got to do, show one function is bigger than the other. We start with something very basic, just the idea of what in the world these things look like. Are you guys with me so far on the idea, at least? Hello, yes, no?
Yes.
The idea, of course, is we've got to show this first. That way we can make some determination as to whether this is happening or whether this is happening. Does that make sense to you? So we start with something very basic, like this. I know just from my trigonometry that sine x is always less than or equal to 1. I know that. Don't you know that? Okay, now here's what's interesting. If I square both sides of this inequality, it should not change that inequality. So what this implies is that if sine x is always less than or equal to 1, then sine squared x is also less than or equal to 1. When I square a number less than 1, or equal to 1, it gives you a number less than or equal to 1. Does that make sense to you? Cool, okay. You sure you're okay with that one, right? Cool. Well, let's just do something really easy. You know we can do anything we want to as long as we do both sides of an equation, and same thing with inequalities unless you divide or multiply by a negative, and then it flips inequality around. So what I could do basically is say, hey, if this is true, then what I can do is, let's just add x to both sides. So if I add x here, and I add x here, I'm going to get x plus sine squared x is less than or equal to 1 plus x. Quick show of hands if you can follow the algebra on that one. Now, did you see the way I came up with this function now? I thought about it like this. Okay, you know what? Sine's always less than or equal to 1. Sine squared is always less than or equal to 1. So I'm trying to build something from this one. So I'm saying, hey, how can I make this function from here? Well, hey, that's bounded by 1. Therefore, this thing is bounded by 1 plus x. That's the idea. Now, of course, what we're going to want to do is, well, we got to reciprocate these two things, put them over 1. If you reciprocate your inequality, if I do 1 over x plus sine squared x, and I do 1 over 1 plus x, tell me what happens to an inequality when I reciprocate both sides. Do you know?
Changes.
2 is less than 3. If I reciprocate, 1/2 is greater than 1/3.
The inequality.
The inequality flips around. We reverse that inequality. Does that give us the relationship that we want to see? It tells us that, yeah, cool, okay, we know that something's happening here, that one function is always greater than or possibly equal to another. Show of hands if you feel okay with this one. That's the idea. You need it to be all the time, too. So we always know that, yeah, these could be equal at some points, but other points, this is going to be greater than this function. Does that make sense to you? You sure? Any questions or comments before we go any further? I need to make sure you guys get with this, okay? So the first thing we show is that I don't know right off the bat whether one's bigger or smaller. Now, I do because I'm doing the problem, okay? But we're not going to know that right off the bat. We got to look at it and go, okay, how am I going to get this thing from this thing? Well, figure it out. Figure out some relationship. Start small. Grow your function. Grow it to what this side is, then compare it to what this side is. Well, this one turned out to be always bigger than that. So what are we going to try to show? Let's think about it. If this thing, please listen carefully and think carefully on this. If this thing converges, if this thing converges, does it tell you anything about this thing?
Yeah.
No.
If this converges, does it tell you about this?
No.
Here's a scenario. It says, hey, suppose that g of x converges. G of x is the small one. If this converges, could f of x diverge?
Possibly.
Absolutely. You don't know. So if this small function converges, we've said nothing about the big function. Does that make sense? Contrapositively, if the large function diverges, does it tell you anything about the small function? No. No, it doesn't. This could easily diverge, and the small function could converge. What happens is, if the big function converges, the small one has to. If the small function diverges, the big one has to. Maybe watch that about 14 times so it actually sinks in there, okay? Because that has to happen. So in our case, if this one converges, nothing. Nothing. Got it? If this one diverged, nothing. Now, of course, we can't do this integral, so we're going to do this one and then make the comparison. If this one diverges, now think here, if this diverges, what's it tell you about this one? That's where we can make the jump. So we can only show one thing here, if at all. If this converges, it's smaller than this one. It doesn't say anything. It says, yeah, your small function converges. The big one is obviously bigger than that. I don't know whether it converges or diverges. But if this diverges, if the small one diverges, the big one also has to. Does that make sense at least a little bit? Okay, so let's go ahead. Let's see if we can do this integral from 1 to infinity of 1 over 1 plus x dx. Now, that's something we know how to do. What would I do first?
You gotta change your limit.
Limit bound.
Yes. I would say this is an infinite interval. As b approaches infinity, I can change it to 1 to be 1 over 1 plus x dx. Yeah, you can do a u sub. We're going to keep this pretty simple because we're past all this stuff. What this changes to is a limit as b approaches infinity of ln absolute value 1 plus x. From 1 to b. Yeah, of course you can do a u sub on that one. You say u equals 1 plus x, it'd be 1 over u, absolute value u, plug in the 1 plus x before we start our evaluation. Show of hands, feel okay with that one? Let's evaluate. So this would be limit as b approaches infinity, ln 1 plus b absolute value. Absolute value here really is not that relevant. Can you explain to me why the absolute value here is not relevant for us? Say what now?
Will be negative.
Never. Our interval is 1 to infinity. We can't get a negative if we're adding 1 plus a number that's positive, okay? So really here, kind of irrelevant, doesn't really matter. Minus ln 2. Quick head nod if you're okay with where those numbers are coming from. Just some evaluation. Now, let's think about it. Where's b going?
Infinity.
Okay. What's infinity plus 1?
Infinity.
So when you're a little kid, I hate you to infinity. I hate you to infinity plus 1. Ha ha ha. It's still infinity. Stupid kids. Anyway, so infinity plus 1 is still infinity. What's ln of infinity? I always argue with them. Stupid. I really don't. I ignore the little kids, just like they should be ignored. That was a joke, by the way. Totally love kids.
Infinity.
That's right. Back to math. Ln of infinity is, so this goes to infinity. What's infinity minus something really small? So this whole limit goes to, so you tell me something. Tell me something. Now that we've done this integral, is this integral convergent or divergent?
Divergent.
Now we think back to why we did this whole thing right here. If this function is always bigger than this function, let me go through this one more time. If this had been convergent, just not. But if it had been convergent, doesn't say a thing about that. Don't know. Inconclusive. Okay. But if this is divergent, this says that this area goes to infinity, or we can't find it, or something like that. This area is infinity. Area of this. What's to say about that one? It has to be. So should we even bother doing this integral?
No.
Heck no. I know that if I did it, if I was able to somehow magically do this right now, our limit would also go to infinity. Since this function is always bigger than this function, the area under this curve is always bigger than the area under that curve. So if this is divergent, this also has to be divergent.
So that's infinity plus bigger.
Infinity plus, I don't know. It doesn't matter. It's still going to be divergent. What I want to know is if that stuff made sense to you guys. Are you sure? Are there any questions about that at all? Questions?
So this is just telling you if it's convergent or divergent.
That's right. It's not telling you what the area is. So had we gone the other way, right? Had this one been let's just pretend we were able to do this, okay? Had this been convergent, it would tell you that this would be convergent, but it wouldn't tell you what that is.
Yeah.
Okay, it'd say it's probably smaller than this area. So if this comes out to a number, you go, cool, it's probably smaller than that, but I don't know what it is. Make sense? Question?
Will you specifically ask us for that on an exam? If you will use the conversion test to see if these are divergent or convergent?
Sure, I would say use the comparison test. Or compare this to another function. I probably would even give you the other function. Okay. Okay.